All right. Hello, everyone. Welcome to the first of the two streams this weekend. Please write something in chat if you can't hear me or something like this. But hopefully it's going to be fine because we are on a more reasonable cadence with the same software and hardware being used. So I'm going to be traveling for the next few weeks, and I wanted to get a bunch of stuff done. And because of this, we are going to try to do a bunch of stuff this weekend, so today and tomorrow. The plans are ambitious, we'll see where we get to. Last stream, so just to remind people, or if you haven't watched the previous stream, so there's this project that we've been doing for like a while now that has mostly focused on geometry rendering using mesh shaders and all of that stuff. And a few weeks ago, we kind of got to a very, very good spot there. And there was a question as to what's next. And the answer to what's next is it would be cool to experiment with a bunch of other Vulkan features that we haven't had a chance to talk about or try before. Unlike the last few streams, I'm kind of entering uncharted territory in the sense that some of the stuff that we are going to write today, I just have never used. And so there's going to be interesting issues that I maybe don't have great intuition for, but that's kind of how things work. So last time we did glTF support. To a reasonable extent, we did like buffers, nodes, geometry. glTF is a large format, so we didn't do the entire thing. We did not touch textures or materials at all. And so today the sort of aspirational target is we are going to do textures, and then we are going to do materials to the extent we are going to load textures from disk, and then we are going to connect the textures to the shaders, and we're going to sample the textures. But so that sort of implies a material in a sense, but there's not going to be any like deep math or BRDFs or anything like this today or tomorrow. So the hope is today we are doing this and doing this to like completion, as in it works, it's fine. And then tomorrow we are doing ray tracing, which again, very aspirational. I have never worked with hardware ray tracing, so God knows where we will be. But the hope is we do enough bring up so that it's functional, but there's going to be a lot of work to do in the future. So there's not going to be super pretty pictures today or tomorrow, but there's going to be a bunch of Vulkan stuff. Because we are somewhat short on time, I'm going to be cutting corners as before. So there's going to be some code that we write today that is going to be not really production quality, but this is not a production render, so it's fine. And in general, my philosophy is it's better to get something working first and then like make it production ready than to have the first time you run the code to have it be in production quality, because there is issues that you don't see until you actually run something. So it's just better to iterate. So that is the plan for today. Before we start, I did a little bit of work, so just so that people know where we are right now. I did a little bit of off-stream work. It's not super deep, and it was mostly not even related to this project because I had to debug some LOD issues. But to remind people where we are, so we have this glTF scene, we can load it, we can render it, and then we are just outputting normals right now. This is world space normals, and this is without a normal map because we don't have access to textures. The scene has diffuse and normal textures and gloss textures, so we have this information, but we aren't displaying it on screen. So that's the plan for today. And also we have LODs, which on this scene it's not we are like in the sort of, we see the majority of the scene there is not much more to this level than what we see right now. And it's not super detailed geometry wise. So the LODs are moderately effective, but they are effective. And so I did a bunch of work off stream to clean up some LOD stuff that was kind of not working super well, including some mesh optimizer fixes. And I also added a mode to switch the LOD quality so that you can see sort of the degradation more clearly. But by default, the LOD selection works to basically have a 1 pixel threshold. So in theory, there shouldn't be a big difference visually between LODs on or off, with the exception of some 1 pixel deltas on some edges. And indeed, if I switch, so last time when I was switching between LODs on and off, there were some visible issues in some places. And now if I press LOD on or off, the only thing that changes is the triangle count. So that's pretty cool. So if you're interested in what work was done off stream, it's not much, but just look at GitHub stuff. There's some minor optimizations. I did some minor cleanup for some old extensions that I don't care enough about. And and for people on Windows, so I kind of got tired of maintaining Visual Studio projects by hand, especially given that we're streaming all of this from Linux. So I just removed the Visual Studio projects, but CMake should just work on Windows without issues. Yeah, some LOD fixes. It's not nothing is super earth-shattering, and it doesn't have anything to do with textures or materials. And I did some mesh optimizer fixes, which was good because, you know, mesh optimizer is now better. The only thing I talked about last stream, in addition to the LOD stuff that was like an issue, was performance of loading. So I added this mode fast equals 1, which loads the scene faster. As I talked about on stream last time, in general, we are loading the glTF file right now. And then we are doing a bunch of pre-processing. So we are doing optimizations for vertex cache, we are doing vertex merging, we are doing simplification. So we generate this LOD chain, we are doing meshlet decomposition. All of this stuff takes time. And so ideally, you would pre-process all of this and then save the geometry blob into a very, maybe compress it, and then save it into an on-disk blob that's like really fast to load from. We are not doing this yet. We might do this at some point, but I want to first do the ray tracing stuff because BVH building will also take time, and BVH data is basically, let's say more difficult. I'm not sure if it's fully impossible, but like let's say it's more difficult to cache. So based on that, we'll see what would make sense there. But for now, I added a fast mode which skips or most of the time that was spent not in our code, but in Mesh Optimizer code, because most of the heavy lifting is done inside Mesh Optimizer. And Mesh Optimizer, for a few algorithms, it actually has a pair of algorithms. One is maximizing the quality of the output, and is reasonably fast. Like it takes us like 3 seconds to load the scene with like a few million triangles, etc. from just a raw glTF file, which is like okay, but it's not great. And so Mesh Optimizer has a bunch of algorithm replacements that go faster at a slight reduction in quality. So I did that, and there is now a mode to like optimize for loading time, but because we are gonna be loading a gigabyte of textures on the stream, maybe all of this is not like super useful and it all is like slow anyway, but we'll see. It's still 1.5 seconds because I didn't want to touch simplification. There's not, you can like remove attributes from simplification, for example, but then the LOD selection gets very, very different. So I didn't want to touch this. Anyway, so that's kind of what we have right now. This is the picture we can render today, and or we can render, I guess, right now. But at the end of today, I'm hoping that we render the picture with normal maps and actual albedo textures. So that is the plan. So to load textures, we need to do two things. One is we need to actually load textures, as in we need to create Vulkan texture objects in memory with the correct contents. And then the first thing, and then the second thing we need to do is we need to expose them to the shaders. Now, people who have watched this for a while and remember this know, but people who don't should know. what you have right now on screen is two draw calls. It's sort of one, but it's sort of two because there is two pass occlusion calling, but the second one doesn't render anything with static camera. So let's just say it's one draw call. Now, if you disable mesh shaders, it's technically a one like multi-draw operation. So it's one command that you dispatch to Vulkan, but it's multiple draw calls, but they have the same data that's passed to them. But if you enable mesh shaders, we removed all of the draw call splits a while ago because they were hurting AMD performance on very, very geometry dense scenes. So this is one draw call. This creates a problem with passing the data, the texture data, to the shaders. And the solution to that is the bindless stuff. So I'm going to talk about bindless a little bit later, because first we need to actually load the textures from file. Now, glTF in general as a baseline format only supports PNG and JPEG. And I'm not going to decode PNG files on stream. PNG is a format that's fine for non-real-time rendering, but for real-time rendering, it takes a while to load from disk because of the decompression that has to happen. And when you load the PNG from disk, you get RGBA pixels, you get 4 bytes per pixel, 32-bit. That doesn't seem like a lot, but that's actually a lot when you consider a lot of 2K, 4K textures, etc. So GPUs have employed block compression techniques for decades now, where you have a 4x4 block of pixels that is compressed into fewer bytes than the uncompressed representation, with some quality loss. But generally speaking, the quality loss is small enough that you should always use them if possible for offline content. So glTF by default doesn't support this. Now, this scene actually uses an extension, a Microsoft extension, MSFT Texture DDS, that has DDS variants for every texture in the scene already. And they are encoded using a BC7 format, which is like a... I don't want to go too much into the specifics of the texture compression because I'm worried people will not have enough time, but maybe we'll talk about this if we have enough time later. So we could use this extension. The other thing we can do is, I played a little bit before this streams with... don't recall where this is. Yeah, so I played a little bit with a tool called etc pack, which is called etc pack, but it actually can compress into a variety of formats, not just etc. And it's very quick, and so it's fairly practical to just recompress the entire texture set. Let me, it has this weird, hold on one second. -H, right? So it like defaults to PVR format, which is cute, but we will not explore this today because it's a little unconventional. The scene that I'm using, the Bister scene from NVIDIA, this is a scene from NVIDIA. It already came with DDS textures, so it already has high-quality BC7 textures. Unfortunately, it doesn't have the original textures. So what I did before is I decompressed things into PNG so that I can open the scene in Blender, but I can also then recompress things back into DDS. Generally, you shouldn't do this because it's not great for texture quality, but I'm just saying this to note that we have this glTF file with a bunch of PNG data, and we could just recompress all of the textures back to DDS. And with etc pack, it's not too slow. It's like an offline process, but it's decently fast. Let me run this right now. Where is this file again? Sorry. Oh, yeah, okay. So this is going to load all of the texture files. I have this weird hack because etc pack doesn't support non-padded textures. And the original scene had like 1x1 textures. Doesn't matter. The point is, if you want to start from the PNG data, you can compress things offline. we happen to work with the scene that already had and is finished. It already had DDS files, but in general we are not going to be working with PNG at all outside of like the compression script or whatever. Maybe I should actually commit this. I will commit this script later, just so that it's like available just in case. Anyway, so now we have a bunch of textures, so we can find them, and then how do we do this? I guess we do it like this. 4 gigabytes? I thought it's not 4 gigabytes. Hold on, that is odd. Oh, I have redundant. All right, hold on. So let me dump this because I don't actually need it. So now it's 2 gigabytes of textures. Was it 2? I thought it's 1. It is 2. Huh. All right, I guess we have 2 gigabytes of textures to load. This is why you don't want to do stuff like this with PNG data, because like decompressing all of this to memory and then spending, so BC7 is 1 byte per pixel. This is not optimal in the sense that for color textures often half of a byte per pixel is enough. But for now we'll stick with BC7. If this was not compressed, this would have been 4 bytes per pixel, which would have been 8 gigabytes instead of 2, and that's like a lot of video RAM to fill, and just in general a lot of RAM. So you do want to stick with compressed textures as much as possible. I thought I ran the numbers that it was 1 gigabyte, but whatever. 2 is fine. I don't recall actually. I think it's an 8 gig. We're using like an 8 gigabyte VRAM GPU, if I recall correctly. Like we should be able to load all of this into memory. It should be fine. And if not, there is the classic trick where when you load a texture, you skip the first MIP, and then the texture is way smaller. Anyway, so to create all of these textures, or rather to load them from disk, we will just open the file, read the header, parse the header. There's like libraries for working with DDS files. I looked briefly. It's interesting that it's in the resources. Oh yeah, okay, that's fine. I looked briefly at like one library, considered maybe we should use it, but then DDS files, all of these container files are simple enough. It's just a weird header and then a bunch of data. And so I figured, hey, maybe it's fine. We can just load them. It's not like a big deal. So let's start writing this code and then kind of see what happens. I'm not sure how much time this will take, but so the first thing we need to do is we need to extract the actual paths from our, we are like completely ignoring the image data right now, so we need to extract the actual paths. Oh, there was this problem with, there's a small problem with the specific scene that we are using right now, which is, it like duplicates. How are we gonna do that? Okay, that is actually fine. So for now, I don't want to overthink this. I just want to load the data from disk. To load the data from disk, I want to just extract the paths to textures. And then we're going to consider the implications a little later. Like there's some weird stuff that we'll have to work through. And I don't want to do all of this like inside the load scene function, so I'll do, I'll like extract the paths and then we will load them separately. So, and this is the case where it would be easier to work with a smaller scene for testing, but I don't have a smaller scene and I haven't prepared a smaller scene, so we'll just roll with this and see what happens. So the way this works in glTF is you have materials that reference textures. Oh, yeah, okay, wait, never mind. Yeah, okay, the glTF structure is actually fine. There is the minor thing that I will not explain because it's too much effort, too much time like to talk about this right now, but there was a quirk that I thought maybe it's going to be a problem, but it's fine. Some of the stuff for glTF loading is suboptimal. glTF is a reasonable format, but there's some issues with this that make it a little bit intricate to write an optimal loader, which again is why you want to do all of this stuff offline. But for now, this is fine. So there is this texture object, and the texture object basically has a reference to an image and a bunch of other stuff that we are just going to ignore. Technically, this will not work for some assets with extensions, but we are not going to bother. And then the texture image is like a URI. It's like an object that has a URI. URI is like a URL, but I guess without a link, I don't know. Now, ideally we should handle this ideally, but I don't want to. For now, we are cutting corners. We might at some point like make all of this stuff more robust, but again, the goal today is as quickly as possible get working code that renders an image and deal with the consequences later. Let me see. So the only other issue is the paths inside the file are relative to the file, to the path to the file, if that makes sense. And so we need to concatenate them. I thought glTF had some helper for this, but maybe I'm wrong. Maybe it's only internal. Let's see. How does this function work, for example? Hello. All right. My editor is not cooperating with me today, which is fine. There's some issues with ClangD and like navigation through symbols occasionally that I haven't looked into too closely. So it uses this function. Yeah, so is this private? Oh man, this is a private function. Okay, that is fine. I guess this is acceptable. Let's just take and then yeah, well, it's a URI, it can't even have backslashes, it must be a forward slash. So if there is a slash, then we are gonna truncate at the slash, and otherwise we, is that, I mean, this is fine, I guess. And then iPath plus equals image URI. Ideally, you should decode the URI. because it can have like Unicode characters and stuff. Is this a public function? This is a public function. Let's see. Yeah, okay. We can just we can just do this in place. It's fine. All right. So technically, this is probably the full path to the file, and this is just boring path concatenation. I doubt people who came to the stream are excited to, you know, work with. Oh, the other thing I should do is I should switch. Wait, what? Hold on. All right, I already had a print, so there's 2 prints. Okay, so these are the texture paths. Now these are the paths to the PNG file, right? As we discussed, we don't want to deal with the PNG files at all. For now, we are cutting corners. So we will just do it's fine. Is there a replace? There's a place. Yeah. Yeah. So rough code, we'll need to rework this a little bit in the future. So you could have, okay, you know what, whatever, let's just do the right thing. The only problem with doing the right thing is the dot is like, okay. All right, let's do the right thing. That's fine. Surely this is okay. And then find the dot. You know, in some other languages you would, so C++ technically has like path objects now, but I find issues with path objects. Not the last one of which is that it's going to be path objects use different characters, and like they use white characters on Windows and non-white on Linux, which debatable to the extent this is correct. Debatable the extent to which this is correct, but so I just don't want to deal with this right now. Hold on. So I guess UI size minus dot. Does place even work? Because it's, no, it should probably be fine. All right, let's try this. This will handle like JPEG extensions and stuff. Okay, so we have a bunch of paths that point to the DDS files. Again, technically you could parse the extension. The reason why I don't want to parse the DDS extension out of glTF file is there's going to be files without the extension, and there's few tools, there's no tools. I mean, there's probably some tools, but it's difficult to find tools that can work with this specific extension because it's a Microsoft extension that never kind of went to further in the standardization process. And I think it might be deprecated now or something like this. Like it's not super mainstream. And unfortunately, glTF has not standardized a different extension that would allow working with compressed files like this. other than Basis extension, which has its own issues. So so for now, we'll just hack this. It's fine. Maybe we'll come back to this. So we have a bunch of paths. Now what we need to do is we need to actually load, where was this? And let me hide this thing. So we have a bunch of paths, and now for each one, we are going to open the file, read the DDS header, and then read the texture contents, and then actually create a Vulkan object with that contents in memory. So for that, I will switch to debug, because if we have any validation issues with Vulkan or anything like this, I'd rather like catch them first. And we will start loading the textures. Debug, unfortunately, is a little slower, but you know, such is life. MD Compressor is, I would not recommend it. There's more issues there, but also I don't think, does it work with MSFT texture DDS? But the bigger issue with Compressor, I think in general it's difficult to find really good compressors. There's all sorts of issues with various ones. etc pack was like simple to build and it supports a wide variety of formats. Usually you would use BC5 for normal maps. This file from NVIDIA comes with every single normal map as BC7 and every single non-normal map as BC7. You can actually, for people who are using Linux, the built-in file command supports DDS, which is funny because it's like a Microsoft format, and DDS support is very poor in Windows, as far as I recall. But yeah, DDNA is a normal map, and it's a BC7. I haven't actually... Did I look at these files? I don't recall. We can look at some of them. Yeah, so see, this is the PNG decompressed from the file, and it's just a regular normal map. So yeah, so BC5 is a little better for normal maps. BC5 is a 2-channel format. But BC7 is passable, and again, because the source data isn't BC7, we can't get better quality than BC7 like at all, because we just don't have the higher resolution, higher quality source assets. And BC5 and BC7 are the same size. So for now, it's fine to use BC7. I think eventually, just to conserve memory, I would switch. Because it's like 2 GB of textures, you know, like if it were like 1.5 GB of textures instead of 2, that would be nicer. So I would switch some textures to, but to BC1, because like from BC7, you can't get smaller unless you go BC1, and BC1 is not good enough for normal maps. All right, so we have this create. Let me look at what we have. This guy probably doesn't do. Interesting. Okay. Let me look at the code that we have to see if we want to reuse any of it. Oh yeah, of course, because we, okay, this is fine actually. Okay, this is a good function, I approve. When you work with Vulkan in general, you should expect to write a memory allocator or use another memory allocator like Vulkan memory allocator library, so that you don't have a single allocation per resource. We are cutting corners, so for now we're going to make a memory allocation for every resource. This is fine for render target type resources, generally speaking. It's not optimal for resources that you have a lot of, such as textures. But I don't want to write a memory allocator, I don't want to integrate another memory allocator right now, so we're just going to do the simplest thing that can possibly work, which is what we already have a function for, which creates a texture. So let's actually start from that. That is a good place to start. So we're gonna have, the only thing is, Oh, it has this, we have this image object. Oh, that has the view already. Oh, this is perfect. Okay. Okay, this is actually great. We wrote some scaffolding a while back for like render targets, and most of this we will be able to use as is for this. So the goal is we will create these image objects, and then at the very end, someplace wherever we destroy everything else, like here. We will destroy them, and then so to create the image, we need to know the height, width, format, etc. And all of this stuff is in the file, in the header. So let me and then presumably we'll need device and stuff, and then so for now, actually this should also be, for now we will not handle like if we can't load an image, we will just bail out. And this is only because what I plan to do is I plan to save for now indices into these vectors inside the scene objects. And so if there isn't one, if there isn't an image, we'd have to like replace it with some dummy image so that the shaders can still access some reasonable data, and I don't want to do that yet. So anyway, cutting corners. And then images push back, and then we just simply have to write this very simple function. This is sarcasm. And of course, we will assume that we are only working with DDS files, etc. You know, some of this stuff is not unreasonable. For example, usually engines. So if your engine has a content pipeline, which it really should, which pre-processes data into the format that the engine can then deal with, then this can allow you to move a lot of complexity from the engine into the content pipeline. This is way nicer because it means you have code that you don't have to ship to your users necessarily. You could even write it in a different language if you want, like you could write your content pipeline in Rust, but your engine in C++ if there are some issues with Rust deploying on, you know, the target platform. It could be somewhat less robust if you want. You could run your content pipeline over a farm to make the iteration time faster, etc. Like you kind of want this separation. And because of the separation, usually the engine really doesn't have to deal with like an infinite amount of image formats that the humanity has come up with. So actually the fact that we are only going to support DDS files is like fine. It's like a reasonable restriction. People do this all the time. It's not a big deal. So we are going to open the file, and then yeah, there's like a bunch of different texture tools and formats that support like various container types, and like unfortunately there's not a very comprehensive one. For example, RenderDoc can open DDS files, I believe. We can check this, but I believe RenderDoc can be used as an image file format. Let me hold on. I don't actually know where this is. Oh, like maybe you have to open like texture viewer, and then inside it there's a load button someplace. Open. Okay, I don't actually know how to do this in RenderDoc, but like I heard it can be used as an image viewer, which is funny. Anyway, But compression is difficult. Like you want to compress it simultaneously reasonably quick. Like it took like several, I don't know, like 10-15 seconds to compress like gigabytes of textures with DTC pack, which is awesome. But at the same time, you want it to produce reasonably high quality results. So it's a tricky balance. So what are DDS files? DDS files are a header followed by, unfortunately, sometimes another header, followed by the actual data. It's a little rough. This file format dates back to, I don't know, like to direct draw. I think DDS stands for direct draw surface. I don't know how many people on the stream know what direct draw even is, but it's like a very old Microsoft API for basically 2D graphics that basically allowed you to get a buffer that you could write pixels to, and that buffer would then display on screen. And there wasn't a whole lot more than this. So all of this stuff is like old, right? But it's okay. I mean, all right. So there is a header that has, like width, height, mip maps, stuff like this. And then this is hilarious, like 128 bits of caps, and then 32 bits of more caps, I guess. I don't know. So this, I don't recall what this is, but I guess we need this. Oh, the other thing I was meaning to, like, this code base doesn't use Clang format, and I kind of tried to switch most code bases that I work on to use Clang format. Is there? Yeah, no. And because the formatting is disabled on this code base, my editor doesn't do an auto format, which is annoying. But at some point, we will migrate to Clang format. And then reformat the whole thing. Yeah, that's beautiful. Okay. All right, fine. So the issue with the DDS format originally, as it was originally specified, is it could only encode some number of formats. Via this 4cc thing, for example, it could encode BC formats like BC1, BC2. They were called DXT back then. This was not quite sufficient, so Microsoft added another header to this file, which I swear they probably could fit this data in one of these reserved bits or something, but it's fine. So I don't recall if the files we work with, like what they use. And these are some enums that are probably, these are all UINT basically as well, yeah. Oops. So this is the DDS file. So it has this struct, and then sometimes it has this struct as well. I forget how you tell. There is some bit somewhere that tells you if there is a second header sort of to read. One moment. Yeah. Maybe, oh yes, 4cc, yeah. Okay, so when 4cc is set to dx10, which is not even a portable way to specify this constant, but whatever. I forget if C++ fixed this part. No, I don't think so. Maybe they didn't, did they? I don't recall. But if this bit is set, then you have like a second header to read. Anyway. So let's read all of this, and then we'll do some minimum validation on the texture data, but not like too much. Because again, I don't want to spend too much time doing all of this. We are already like 40 minutes in and we haven't even started reading the files. So, except that I kind of like this. Yeah, 0 is fine. Oh, does it return int? Some, yeah, okay, cool. So this will just automatically free the file so that we don't have to like remember to do this. All right, and then we have dxt, this guy, and then so this is that, and then in theory we have the header loaded, whichever one. The reason why we need the second header is that for formats like BC7, the format is actually in the second header, not in the first one. Again, it feels like unnecessary complication to me, but well, I should say, like, it would be nice if the DDS file had, oh, hold on. Oh my God. So they had like 44 bytes of reserved data inside. I didn't even know that. It feels like they could have just put the second header like inside this or something to make it slightly easier, but it's fine. Who cares? A few extra lines of code. So, yeah, ideally we would validate some stuff. We definitely need to validate the the size, just to make sure that things are correct. I will ignore this. How does this work? Right? Surely that's a weird struct. Huh, okay. All right, that's fine. Is it actually 32? Yeah, okay. Okay, and then, so we have the width and height to create the image. DDS files couldn't code cube maps, they couldn't code volume textures. I don't want to deal with that. They have this weird, it's been a while since I've written a DDS loader. There is this weird, yeah, there is this cap structure that essentially tells you what the file is. So you shouldn't just say, oh, the file has, like, the file specifies a depth that is not 1, it's a volume texture. There's caps that tell you what the structure, what like the contents of the file is. So we are not going to support any of that, obviously. And this is dv caps 2. And again, like, so this is the type of stuff that you actually would want to fix in a production render, because you probably want cube maps and volume textures and 3D textures, but we don't. So now that that is eliminated, this stuff we can just ignore probably. All of the other caps, I think we can just mostly ignore. I don't even know what they stored. See, there's so many unused bits in all of this stuff. It's insane. Why didn't they just put things there? Okay, anyway. So the other thing that we will shortcut on or cut a corner on is I don't want to support. There is stuff you can store in DDS files that's like difficult to load. For example, you can have uncompressed textures with, I think, 24 bytes per pixel, 24 bits per pixel, like 3 bytes per pixel. Yeah, like this. And there's these masks that tell you kind of how to, anyway. I don't want to deal with all of this. I just want compressed formats. And the only reason why, when you are working with textures, when you're working with BC7 textures, you're guaranteed that you have this header because there is no way to encode the BC7 texture without this header. When you're working with BC1 textures, you may have this header or you may not have this header. So that's like the only reason why I sort of care a little bit about the like the early, the like legacy parts of the header of the DDS file. But I guess I should check this as well, just because why not? Because maybe there's like, oh wait, what was this? 3. Okay, so that is done. I don't actually know if the metadata can be conflicting. It's fine. Oh, misc flags too. I see. Okay, this is fine. Okay, I think this is kind of it as far as validation is concerned. Let's actually run this code to see whether we are, yeah. Okay, that's actually fine. We will fix this later. In the good old days, people liked to use these 4-character codes, but C++ didn't like specify the behavior for them for like a while, and I haven't kept track, so I don't know if today the objects are specified or not, like the values are specified or not. All right, so we have some bug in oh, this is the bug. Yeah, there's a warning. Cool. No, there's more bugs. Okay, let's actually step through this then. Let me look at chat while we are doing this. Is DDS and KTX similar? Yeah, they're kind of similar. I mean, both are basically, there's some header with some encoding, and then it's followed by the actual bits. So the formats are different, the headers are different. Some stuff you can't encode in DDS that you can encode in KTX, like ETC or ASTC files, but like it doesn't matter. It's kind of the same. Clang format works fine with Almond style? I don't know. I use Almond style and I use Clang format like on many code bases. It's fine. There is some minor bugs, but there's a bunch of bugs in Clang format about a bunch of formatting choices. Yes, I use I use dynamic rendering. We talked about this before. Forget when, but watch previous streams. I could use KTX2, but the problem is the tool that I'm using right now to encode textures can't output this. And it's going to be roughly the same code anyway, you know, it's fine. And DDS support is better, generally speaking, in viewers. I find in KTX2. KTX2 is a very recent format. So, ooh, what? Whoa, hello. Oh, yes, there is a magic. Oh boy, hold on. We forgot the magic. And it's not part of the header and the, okay, fine. So there's also magic. Wait. Which should be equal to, I don't know if this is right, but it should be equal to, it's not here. Yeah, so the file doesn't actually even start with the header structure. It starts with with DDS space probably, right? Yeah, it starts with DDS space. Yeah, this is actually the correct constant. All right, and then after this you have the header. Okay, so the texture headers can be parsed. That is fine. And then we have a bunch of errors because we didn't actually create the image, but we told the code that we did. So of course that's not cool. So we're gonna fix this. Let's create a helper because oh yeah, this is actually fine. Yeah, this is correct. Oh, right. Yeah, sorry. The problem with Copilot is sometimes it's right and sometimes it's wrong. And when it's wrong, you have to like let's do this so that it's guaranteed to be like a zero terminated array. And then let's use this, wait, go away. Here, and then here, and then somewhere else here. 4cc literally stands for 4-character code. Self-explanatory. All right. So now that we have the header, now that we've validated everything, everything seems fine. I'm sure there's other sanity checks that you could add here, but we are gonna ignore them for now. So then the next thing that we need to do is we need to actually create the image. And for that, we will just use the function that we've written like at some point. The function returns void, so it can't fail. This is a lie. But you know, again, at some point we'll like uncut a bunch of corners that have been cut before. Oh. Huh? What is that? Do I just have this? Oh, yeah. Okay, got it. Yeah. I don't want to explain everything that I'm doing here, and the things that we are doing right now very, very early on. Oh my god, physical device memory properties. And it's probably not small. Oh, I don't have, interesting, okay. So, but like at some point in one of the first couple of streams, it might have been the first or the second stream, we talked about like memory management and all of this stuff. So rewatch that if you need to. And we are going to do some more actual allocation tomorrow for ray tracing if we actually get stuff done today. So anyway, so let's do this TV height and then header mipmap count. I think mipmap count might be off by 1 because it might be the number of mipmaps except for the first one. I don't know. Don't really know what to make of this. I should have. I'll look in debugger, and then we need the format, and then we need usage flags. So the only reason why we are creating the texture is that we are going to sample it from shader. And for that, there is the sampled bit. But the in addition to creating the texture, we need to fill it with data. The way you have to fill textures with data is by copying to them, which implies this bit. So we need these two bits. Vulkan has one extension that can make image loading more straightforward. I was excited to use that, but unfortunately my drivers don't support it. It's usually an extension that's helpful for integrated GPUs, not a dedicated GPU, so that's fair enough. But you know, unfortunately, we can't use it, so we're going to use whatever we can. All right, so the only thing that we need in addition to all of this basic stuff is the format. And the format is weird because, of course, the format is encoded in a DDS file differently from, it's not like a Vulkan enum. So let's just do this. All right, so if we have this dx10 thing, no. Or actually, this is fine. Yeah, so the way DXT, so BC, oh my God. Do I explain this? So there is a bunch of compressed formats, and BC stands for block compressed, and they all this format that packs like 4x4 bytes, 4x4 pixels into like some number of bytes. Before BC, there was DXT, DirectX texture compression, and before that there was S3TC. And there's some overlap, so BC1 through 3 used to be DXT1, 3, and 5, with DXT2 and 4 suffering an unfortunate fate. And so because of this, if it's a legacy file, we have to like check if these are used. And also there's some sRGB stuff that is gonna be important, but we are not gonna deal with right now. So effectively, we just need, oh, and there's also RGB8. There's so much weird legacy here that like it could take a stream, an entire stream, to like talk about why and what the differences are and stuff. But we are short on time today because we have too much, we have promised too much, so we are not gonna do that. Okay, and then if it's a DXT, or if it's a DX10 thing, then the 10 header has this DXGI format that actually specifies the format. And that's, of course, not a Vulkan enum either, and instead it's this enum. And we'll need to steal some stuff from here. Should I just enum this? I should just enum this. This typeless stuff can't happen really in the file. These we need 4, 5 we want, and then we are gonna do 6 and 7. So 7 is a very versatile format that can be used for what's called low dynamic range content, so data between 0 and 1 in 4 channels. But there's also BC6, which can be used for HDR textures, which we don't really need. I don't think we'd need it because it's like used for like environment maps for HDRI and stuff like this, which we don't have and probably won't have. So we'll probably ignore this, but for completeness, it's just a switch case to like remap some stuff, so it's fine. And then it's not super correct to just ignore the sRGB stuff, but we are going to talk about sRGB at some point, like, I don't know, when I return, because it's irrelevant right now. What the heck is up with the indentation? Okay. It's weird. Okay. So this is 3, and then this is, well, here you do have to distinguish. It would be incorrect not distinguish. And then this. Oh, is this the recent? I see, okay. Anyway. We won't have like a way to test most of this code because obviously we are only handling a subset of formats. We only have a subset of textures, etc. But it's fine. Okay. So in theory, we are now ready to create the texture objects in memory, which is when we will find out, do we have enough VRAM, you know, can we actually do this? But we should have enough VRAM. Okay. It takes a little bit of time, but it's like debug and stuff, and all of the geometry code is still running. So, oh, and we now can exit without hitting a validation error, so we presumably create the objects just fine. Okay. Now, in addition to creating the objects, we need to actually load the data from memory, obviously. The way you do this in Vulkan, and we already talked about all of this, like very, very beginning, very, very early on, but you have to copy the data to a Vulkan buffer object. And then you have to copy it to the image object using command buffer, unfortunately. The reason why I say unfortunately is that it's like what you thought was just creating the texture object is now actually recording commands for the GPU to process and using extra memory and stuff. So we have a shortcut for this that we used, which we are going to repeat because I don't want to invent, I don't want to write very complicated code, as I was already saying 5 times. I want to start by writing simple code. And simple code is very inefficient. There's a to-do here that, you know, has been here for a while, which we should fix at some point. But what this code is doing is essentially it's submitting commands to upload the data and then waiting for these commands to finish. This is not great, but, you know, it's a decent start, and then you rewrite all of this code in the future. To do that, you have to have a buffer that you can actually copy the data from. And this is going to be the buffer that we actually read the data to, because we haven't even read the bytes of the object, of the texture. To read the bytes of the texture, you have to ask how many bytes do you read. The answer to this is a little annoying because you have mipmaps and you have textures that may not be power of 2 and stuff, but like essentially we need the function that will tell us for a given format sort of how many bytes how many bytes per pixel, how many bytes per block really in this case do you need? I guess we are gonna shortcut all of this stuff again. So, well, so given a texture, given a block compressed texture, with a given number of MIP levels. Oh, I haven't checked the MIP levels. We are going to check the MIP levels right now, because what we'll do is we'll read the texture data, and then if we haven't read the entire file, we will say something is wrong. There is some data at the end of the file that we haven't processed. This must be a bug. This is not necessarily, it's not always good to do this kind of check, but it's often good to do this kind of check. So, and yeah, for now I'm only gonna do this for block compressed textures to not deal with like other stuff. It's all fairly simple to adjust. It's just a little bit of math here and there, but and I guess it's good to, in theory, you may have a texture, single texture that's more than 4 gigabytes. Do drivers work with these kinds of textures? I doubt that. But, you know, just in case, this function will be correct. So the way this works is that you have to compute the number of blocks, and the way you compute the number of blocks is all blocks are 4 by 4, so you need to divide width and height by 4, but you need to first round it up, because you can have like a block that's only 3 by 3 or 5 by 5 pixels, or not a block, like a MIP level, and then it's split into, for example, 2 by 2 blocks if it's a 5 by 5 texture, 5 by 5 MIP. So you have to round up before dividing, multiply by block size, and then basically that, except that this needs algorithm. And you don't need that header necessarily. So then divide by 2, keep going. Well, you could have partial MIPs, so this is fine. And then for now, there's all of these 7 block formats, but only one of them has 8 bytes per block. All of the other ones, 2. And this guy comes in 2 halves. All right, that's fine. So 2 formats have 8 bytes per block, so half a byte per pixel. It's either BC1, which is a color format, or BC4, which is a single component format. So it only encodes a single channel, so it only needs like half a byte per pixel. All of the other ones need 16. So then image size is this guy, and again, I'm not, MIP count might be off by 1, we will find out in a moment. So then to actually process this, we will read it into a scratch buffer that we already have. So we just pass like a const buffer, I guess, scratch. So this is the part of the code that, while we are cutting corners right now, we might actually come back and rework in the future, not this stream, just because one of the goals of this series, in addition to, I just like doing this, but in addition to that part, one of the reasons why I am doing all of this is to have like a resource in the form of streams that people can go to and learn how to solve like problems. And one of the problems that you need to solve let me do this before actually. When you are writing Vulkan code, is like efficient texture upload. There's a bunch of stuff that we are going to be doing right now which is inefficient, so at some point we will probably want to go and correct that. All right, so we are going to be reading the texture into the scratch buffer, and to avoid complications we will not like handle the case where the scratch size is not enough. No, I did not mean, I did mean just buffer. Thank you very much. Okay, so I guess it doesn't really matter. Do we create the image first? Do we read first? It doesn't really matter. Let's create the image. So now the crucial point where we are actually reading the resources. All of the stuff has been explained before, but because it's been years, this buffer is just a Vulkan buffer. That's just a blob of bytes. But we are creating it in such a way that it's accessible to the GPU, but also mapped to the CPU. So we actually have a pointer to CPU memory for this buffer that we can just like copy stuff to. And if the buffer is not used by the GPU concurrently, which it's not, then this is safe to do. In practice, what you want to do is you want to have either a ring buffer or several scratch buffers, and some of them are used by the GPU right now, so you use the ones that are not yet, and you synchronize all of this stuff carefully and things like this. It's possible to do. It's a bunch of work. We are not going to do this work right now. And then I can never remember. Yeah, okay. So this is the moment of truth. Well, this is not the moment of truth, but so this loaded a bunch of textures, and then it didn't load one. I am wondering, let's just debug this, and then we'll see. So what I want to do is I want to set a breakpoint to texture CP180. And then I don't have the check yet that I strongly suspect map count is off by 1, because I just seem to remember, it's been years, but I seem to remember this means the wrong thing. So let's look at the header, which does not work. Oh, the header. Map count is 12, actually. I'm not sure what it should be though. All right, so let's look at image size and let's look at read size. Yeah, so we read slightly fewer bytes. Wait, why? Is this a compressed texture? I mean, it must be, but it has 4cc, which is whatever the heck that is. Wait, no. We need format. So header 10. So header 10 format is 98. 98 is BC7. It can't be off by 1 in that direction. That's impossible. Hold on 1 second. So block size presumably is 16. That is slightly confusing. Hold on, I need one more terminal somewhere. This is this lumberyard texture. Hold on. This guy. So let's do this again. Yeah, this is too much clearly, because we have 128 bytes of the total legacy headers plus 16 bytes there. Yeah, so image size is too large. I'm so confused. I have a suspicion. Let me validate this suspicion. I think we might have found a bug, but it might not be our bug. I might be wrong. So I'm tracking all of this stuff in Git. And what we have just done is we've used etc pack to recompress all of the textures. It might be that there is an off by one bug in etc pack. Let me try to load the original textures. If that is correct, then we will keep using the original textures. And then, yeah, okay, all right. So we found a bug in etc pack. You know, maybe, okay, I will offline like submit a pull request or something. It's clearly a bug in etc pack where, so this texture was not a power of 2, which means that it's delicate. When you write texture code that deals with MIP maps or block compression or both, you have to be careful. If your texture is 12 by 12, then the first MIP level of that is 12 by 12. So that one is divisible by 4 and by 4 on both dimensions. That's cool. However, the next one is 6 by 6. 6 by 6 is not divisible, but it's still 2 by 2 block grid, because the first block is like 4 by 4, and then you have an extra 2 by 2 sort of pixel border that you have to deal with, etc. So this code is like, you have to be careful when writing this, and it's easy to have off by one error somewhere. So I suspect that we've hit an off by one error in etc pack, because essentially it's encoding the texture that says, oh, there's so many MIP maps, but then doesn't actually provide all of the data for these MIP maps. Anyway, so the one thing I do not recall, I'm tempted to just check this flag. I forget how eoff is set when you like read to the end of the file but not past the end of the file. Let me check. Yeah. What happens if I do fgetC, I think it's called, after this? fgetC returns -1. So you have to read. Okay, so let's do that. I think this is how it's spec'd. I don't remember. Yeah. So this is the thing I was saying, hey, we should check if we are at the end of the file. There's a bunch of ways to check this. There is an eoff flag, but it's not set because we've just read the file, but not the next byte. It's weird. But basically, if fgetC of file is not -1, then this means there's extra data past the end of file, or past what we have read, which suggests that there is a bug. It's not guaranteed, because maybe some tool pads the contents of the file past the end, but none of these textures have this padding at least, and this helps us validate. So we have just found a bug in a different tool that processed these DDS files that didn't write enough data. But just like this, there can be bugs in a tool or maybe in our code that doesn't read enough data. And so it's good to safeguard against this. Okay, anyway, so with that, we have read the data into the buffer that is mapped to the GPU. Now, in theory, we can just copy this horrible code that you should never use in production, but we are going to run anyway. Should I actually externalize? Yeah, you know what? To make this slightly nicer to read, I am going to... I don't have the size. I don't have the size. but this would be actually nicer. Yeah, so let's return the number of bytes that we have loaded. I'm sure we'll hit some weird... There is no way this will work, because we'll need like image header and stuff. Okay, you know what, whatever, that's fine. Bullet is, I just didn't want to pass all of the other stuff to the function, but I guess we'll have to. All right. So we don't need all of that stuff. It's a little ugly, but I'll think about this later. Oh man, we haven't even started doing descriptors yet. I guess it's going to be a 3-hour stream. Okay, so this is not quite the code we need, but this is close to the code we need. Let me close this. Let me... So device pull buffer queue. All right. So to actually upload the data, so we've copied the data to a buffer that the GPU knows about. But we have created an image. But what we need to do is we need to copy the data from the buffer to the image first, and then we also need to do some layout transition stuff. I guess we actually need to do both technically, yeah. So to copy the data, there is a function called cmd copy buffer to image. You tell it the buffer to copy, it generates a command. So you tell it the command buffer, but then you tell it the buffer and the image. And also the image layout, which you have to transition to because it doesn't do general and stuff like this. Okay, so we have like a bunch of helpers for a bunch of stuff at this point, so all of these things are less painful than they could have been. So So the first thing that we need to do is we need to transition this. This is all like extraneous stuff that is just unfortunate sort of side effects of how the Vulkan API works. But the texture that we've just created, it's kind of in an unusable state, like you can't actually use it. And you need to say, I'm gonna transition this to the to a state that the copy command will work in, or to a layout rather. So autocomplete completely gave up on me, which is fine. This is not well-formed code. So the one thing is, wait, oh my god. All right, hold on. I think I'm going too fast. It's hard for me to like, okay, yeah. So the texture after we created the texture, it's kind of in a no state at all. Like we haven't done anything with it. It's not used at all. We have to transition it to the mode where we can write to it, which is transfer stage. We are gonna write in this transfer stage to this texture. And then we are going to transition to the layout, which is optimal for transfer speed. Technically, in some cases, you could want a buffer barrier as well. We don't need a buffer barrier for complicated reasons. And then once the copy is done, we want to transition out of the thing that we just transitioned into the state that we can use to render. Rendering means we are going to read it in the shader. So, and we are going to read it in the shader from like any stage. pipeline stage. I don't even, no, not alt. It's unfortunate that I don't have like, let me just steal stuff from this. Because the issue is I might use it in compute at some point. I guess for now it's just fragment. But I guess we can, all right, for now, let's just do, there's something like all graphics beta or something like this. I just don't recall how it's spelled. And okay, I guess that's how it's spelled. Okay, that's fine then. And then vk access shader read. Something is weird with autocomplete today. I'm not sure what. And then vk image layout shader read only optimal. Yeah, okay. So then we have these barriers, then we need to transition to them. And we have a pipeline barrier helper for that. So this is the first barrier where I think it's like, I forget, buffer dependency flags, buffer barriers, image barriers. Yeah, okay. So we don't need buffer barriers, but we need this one, image barrier. So again, optimally, this code is close to the code that you would write, but not quite there. Optimally, you would batch both the uploads and the barriers together so that in one command buffer, you are uploading a bunch of textures. And then before that, you are transitioning all of them. And then after this, you're transitioning all of them. We might do this at some point. It's just not going to be today. All right, and then we need this copy buffer to image stuff. We're almost done with the texture stuff. The reason why I didn't want to do this for years is because it's fiddly and it's not particularly interesting, but you know, you have to do what you have to do. So then this is our layout. And then we have one region. And then this is our region. I hope I don't have to do this per mip map. Actually, I of course will have to do this per mip map, right? There's no way it will work without. Yeah. All right. So instead of one command, we will have. Wait, is there a buffer? Oh yeah, there's a buffer offset. Cool. All right. So one copy command, I think probably can only copy one MIP level, because otherwise it would need to know how far the MIP levels are in memory, which one comes first, etc. Like etc. So this doesn't work. The way it works is it's one MIP level at a time. Fortunately, transfers and command. Fortunately, everything else, like you don't have to duplicate, like you don't have to submit 15 command buffers for 15 MIP levels. Although I think I've seen an engine at some point that did that, but you don't have to do that. You just need to do a copy per MIP level. And we'll need to record offsets, not just, hold on. That's fine, we are gonna cheat a little bit. It's gonna be a little bit weird, but it's not too bad. Okay, so buffer offset, and then I don't remember how these values work for buffer, for block compressed textures. If either of these is 0, then it's tightly packed. This is fantastic because everything is tightly packed. So we can just specify these are 0. And then we have these layers structure, which is aspect color, and then MIP level, and then I guess this is that. Okay, and then image offset is a 3D extent, and then this guy is the all right, fine. So this is the starting point, and then this is the all right. So this is roughly what it should be. Now we need to do buffer offset. Yeah, essentially we need to kind of repeat the code that we have just written here, which is fine. It's a little annoying because they can get out of sync, and if they do get out of sync, you know, it's not going to be great, but it's okay. So mip width and then mip height. I think there is some trick to let me all right, so I think this is kind of it. The validation layers will complain if we did something wrong. So we do a transition to a state where we can transfer out of, or into rather, the image. And then we do a bunch of buffer to image transfers that copy out of the buffer that we've just did an fread into, copy into the actual object. Actually, let's also do file storage. Was it file ptr release reset? Just to like close the file early. It's not critical because we are going to close the file anyway, but it's just nicer a little bit. So then we submit this, then we submit this command, and then we run the command buffer, and then we wait for it to finish. This is not great. This means that after every texture upload starts, we are waiting for it to finish, which is going to slow the overall process down. Hopefully it's not going to be too slow, even though we have a lot of textures. We might be done with texture upload. So the problem with the code that we are writing right now is that we can't easily check whether this works, except we can run it under render doc, which we're actually going to do now. And then I'll read the chat and then take 5 minutes to like not talk. Okay, so I need to switch well and off for reasons. And then hopefully this still works. Oh, I should maybe enable sync validation to check that our barriers are correct, although they probably are. Let's check. Okay, no errors here. And then let's check render doc. Oops. So do I have to? Yeah, I have to check this thing. I think that's it. All right. All of this is not super fast, but we don't know yet. It's debug code, validation is enabled, and we don't know what is slow, so it's not time to optimize anything yet. So what I want to do is I want to look at, there's a bunch of images, and then they have an image view, and then how do I view contents? This looks like a texture to me, I guess. Let's do MIPS. All right, so this basically works as far as I can tell. We have a texture, it started, this is a non-square texture, which is great. We have pixels, they look reasonable to me. And it has BC7 format, which is written somewhere. Okay. I think we are done with texture loading. Notice we haven't touched a single shader, so we don't actually have access to these images yet. And of course, we have some performance issues in the sense that I'm sure that the shortcuts that we have done don't help us load the textures as fast as possible. So the final thing, I want to commit this code so that we can like revert stuff, etc. later if we need to. But I want to one moment. Hold on. And then I want to remove this print so that the output is cleaner. And that is the code that I would like to commit. Oh, I need to disable Wayland again. Oh, actually the load is fast. All right, so let's do use Wayland on. We can check release mode like later at some point. But whatever horrors we are committing right now, they're not too bad actually. Because synchronous loading, it's not ideal. Like it takes us around a millisecond per texture, give or take. So it's like 300 something textures, 360 milliseconds. I suspect a lot of this overhead is in, it could be in some validation stuff, but it's likely also just in the fact that we are spinning up the GPUs, like submitting commands and waiting for them. The commands are very quick to finish. It's like whatever I said, like 2 gigabytes of textures, but it's not, you know, it could be worse. But all of the synchronization stuff is probably not helping us load them faster. But in the grand scheme of things, our geometry render is like slower, so does it matter? Maybe not. All right. Let me commit all of this. One second. This is like Amazon delivery or something. I think it's Amazon delivery. In which case, I'm gonna ignore it. Yeah, this should be Amazon delivery. They'll figure it out. Okay, cool. That was a speed run. All right, and then of course we actually have this stuff. Day 23. DDS equivalence of the G file by glTF is seen in as Vulkan objects. The process could be more efficient. We consume one memory object per texture, and we synchronously upload each texture one by one to GPU memory. But that can be improved later. And we found what most likely is an etc pack bug with non-power of 2 textures, which we are going to deal with later. All right, so that is the first half. All right, brief pause. Yeah, so XHost image copy is an extension that can simplify the process that we have just gone through. It's not a dramatic simplification compared to the simple version that we've written, because we are cutting corners, so we are submitting work, we are waiting for work, it's all not great. There's this extension which allows you to do the stuff that we are doing without submitting GPU commands. This is helpful because in our case, we are just loading all of the textures before the application starts, which, you know, means we don't care about this is an anti-pattern. You should not do this, because when you do this, you are waiting for all of the submitted work into the GPU at this point. If you do this in the middle of your frame, you're going to have a guaranteed frame spike, almost guaranteed. It's going to be hard to maintain consistent, like, high refresh rate if you do this. You don't have to do this. You could do this more optimal thing that I was talking about, where you have like a ring buffer or whatever. Also, there is some stuff around different queues that you might want to use. This copy, which one? This copy executes on the graphics queue. This is not the biggest problem of this code right now, but if you just fixed this part, you'd still have an issue where this copying code runs on the graphics queue. which means generally speaking on many GPUs it can't run concurrently with shader work, which means that in an application that continuously loads textures from disk, you will have continuous bubbles of like half a millisecond, quarter millisecond, like some number of milliseconds per frame, variable based on however many textures you load, consumed copying data around. You can work around this by using copy queues or transfer queues, as they're called in Vulkan, I think. We are not going to do this today or maybe ever. It's a bunch of work. I don't want to do this. But if you don't want to do any of this, oh, and also, right, and so then if you have an integrated GPU, it shares memory space with the CPU. So all of this work is kind of redundant, but you kind of have to do this. There's no other good way to do this stuff other than linear textures, which will not, they have issues. So yeah, there's this extension that for integrated GPUs, it basically allows you to do preparation of a bunch of the stuff that is done behind our back by the GPU. Not yourself, but sort of on your timeline. Yeah, like you will have a thread that loads textures, and that thread will do a bunch of extra work without talking to the GPU at all, and then just upload ready-made memory. But our driver doesn't expose this extension, so we can't even try this, so we're not going to. So that is that. KTX has super compression, that is correct. It's basically the standard applied on top of UASTC. KTX has benefits, but it's not the optimal. Super compression is fine in some sense, but I think the way it has it defined. No, it has it defined. I think it will work for any format. Anyway, so there's pros and cons of KTX too. But the biggest issue why honestly we're not doing this right now is the tool I found. The tools I found mostly targeted DDS files, and then we found a bug in the tool. So we'll see. I have a typo in UNS and BC4. That is entirely possible. Obviously, we are not working with BC4 textures, and honestly, it's unlikely. BC4, oh yes, I do. Thank you. That will have taken at some point some time to debug if we ever start using this. The BC4 format, it's one channel. It may be useful sometimes. Maybe you have some version of light maps or like occlusion maps that only have one channel, but you often could also pack this someplace else. So I think BC4 is not super commonly used, but it is used. BC5 is frequently used for normal maps. BC7 is frequently used for color textures. BC1 is frequently used for color textures when you don't want too much precision and you want half as much memory. BC3 is very frequently used for textures with alpha, although if you have BC7 you could also use that instead, and BC2 is this old sad forgotten format that's basically not really used. Alright, so let me patch this. Thank you for the fix E11211. So we'll talk about Bindless now. Yeah. I have similar thoughts. So this is, we are not using BC encoder. We are not loading textures from PNG. We are loading textures from DDS files that are on disk. Right now they are, I don't know what they're encoded with because they came with the scene. So we have a set of DDS files that came with the scene from NVIDIA. I don't know what they used, but some NVIDIA tool perhaps, I'm not sure. And then we tried to re-encode them using etc pack and unfortunately hit a bug in etc pack. So if we weren't in a rush, I would have fixed the bug on stream, but we are not going to do this. I'd rather do Bindless. But yeah, like you can load the textures. I should also say off disk is a little bit of a misnomer. I have a lot of memory on this machine and a lot of the stuff is cached. So let's actually see what the performance of this code is for real. Let me first recompile. I don't think this will matter much, but let me recompile in release. I mean, it will matter for the geometry processing, not for texture loading, presumably. Yeah, so the same speed for loading textures. So 0.35 seconds. Now, these are not loaded from disk, they're loaded from the file system cache. If I empty it, which on Linux you can do using this beautiful command, which is totally, you know, which you can easily remember. This is not going to be 0.35. Let's see what it's going to be. This is going to be 155, right? This is the fast SSD. And yeah, I think I said, I don't actually know now if it's how many gigabytes of textures this is. If I load again, of course, it's going to be 0.35 again because it's all cached. We can like add these up, I suppose. Let's just very quickly because we might be like loading a subset of the DDS files because maybe some are left over from, I don't know why this would happen, but there's the reason why I'm not dividing by 1024 to the power of 3 if people are interested. Yeah, it's 2 gigabytes of textures. Okay. So that's fine. I said 4 in the very beginning of the stream, but I think I had 2 copies of the scene with 2 copies of the textures. Yeah. So 2 gigabytes of textures in 0.35 seconds from cache is like fine. It's not too bad. It's not too good. From disk, it takes 155, which is a gigabyte and a bit a second. My SSD can do much more, but for my SSD to do much more, you have to load files in parallel. And maybe without a read with like a map or something, I'm not sure. So this is not the fastest that the system can do, but it's not terrible. It's like, it's fine. All right, let me switch back to debug because we are gonna do bindless now, and that's gonna be validation. That's gonna be the case where validation is crucial. I think there's one more thing in the chat that I missed. 1 second. All right, so. Yeah, okay, cool. All right, so we are now in a perfect position to actually do bindless. I'm hoping I can do this. It's been a little under 2 hours. If I can do this in an hour, then that's going to be good. If not, we might have to proceed with that tomorrow. So with bindless, so what is bindless? Let me close this. Let me close that. All of this we don't need. So we have, I'm not sure where my pen is. Oh, there it is. So we have done this, but we have this remaining, right? So like this is done. The texture part of the bindless textures is done. So I talked about this briefly in the beginning of the stream, but we have now loaded 300 something textures, and we want to sample them in the shader to actually see a meaningful difference on screen, because right now, you know, the screen looks exactly as it used to in the beginning of the stream. All we've gained for our trouble is an extra line in standard output saying loaded 343 textures. So this is one draw call that is using a like 2-line fragment shader or something. This is our fragment shader. So what I want to do is, and of course, so there's some duplication. I've talked about this last time. It's kind of annoying. I will fix this at some point. But for now, I will. Oh, I didn't do, did I do tangents? I did not do tangents. You'll need to do tangents for normal maps. Man. Okay, that's fine. Let me first talk about this. So, so we don't have UVs here, but we can easily pipe UVs through like it's fine. The issue is this fragment shader executes in the context of a draw call that we have one off. And there's many objects here on screen that use a variety of textures. There is a total of 343 textures. I actually expected more because there's around 3 textures per material, maybe 2.5 or whatever, because diffuse normal, I think all of the textures, all of the materials would have it. And then specular gloss, it's 1 texture, I think, in this file, in the scene. combined, but as in one type of texture, but some materials have it, some don't. So maybe there's like 2.5 on average per material, so that's like 150 or something materials. I was prepared for much more, but I guess textures are just high res here, so there's more data but fewer textures. So how do we pass 343 textures to a single invocation of the shader? Because we can differentiate between draw calls in the sense that I have a draw ID somewhere that I can pass through to the fragment shader, but I don't have a texture object that I can bind in the standard Vulkan way, because the way we've been binding resources so far has been, we have been doing this using push descriptors. You can also, push descriptors are, you have like up to 32 resources or something limit. You can have descriptor objects, which I had code for, but then I nuked it, but it doesn't really matter. But the point is, like, you want a lot of descriptor objects. So what you want really in the shader is you want an array of textures. So what I want to do is I want to do like textures and then some large number here, ideally no number at all. And then here I want to do, haven't written JLSL in also a while. Hopefully Copilot will carry me. All right, this is garbage. This is not doing the right thing, but it's fine. So, all right, yeah. And then ideally, instead of sampling the texture number 0, which I'm not sure if I can, binding, yes. Yeah, we'll fix this, this is fine. So ideally, instead of 0 here, there would be something else. For example, there's kind of better ways to do this, but for now, let's just say I had a material or like a texture ID here, and then I passed it here. So this is, yeah, flat and yeah, cool. This is where I want to be. So ideally, I would want to pass an index somehow to the fragment shader. This would pass it from like the first vertex. You can also pass it per primitive, which is a little faster on NVIDIA. I think it's probably the same on AMD, but I'm not sure. But you can pass, like we can pass, you know, we need 3 textures, for example, it'll be the normal map and gloss. We can pass 3 textures. We can pass a material index, and instead of decoding it and passing more and more data, we can sample the indices to textures from some array and then use them. But the crucial question is, we have an index. How do we sample from a texture with that index? So this is where there is some dragons with the original Vulkan binding model, which has a bunch of restrictions on arrays, on large arrays of textures to sample from. So there's 2 extensions that are relevant, but we are only gonna really have time anyway to talk about one today, which is descriptor indexing. So what I want is I want a large array of descriptors, and then I want to pass this entire array to the shader and then index it. It's notably different from a texture array. Texture arrays have restrictions on the format. It has to be like the same format, etc. for all elements, same size. Here we have different textures of variant sizes, etc., etc. We want to sample the right one and then use the resulting pixel color in the shader. So this extension helps with some aspects of this. We don't need all aspects. For example, one thing that this, or right now at least, one thing that this extension allows you to do is this update after bind. And update after bind means that you have this giant array of textures. What you want is inside an application is you allocate a big array, and then you bind it to all of your shaders that need textures. And then independently of this, for example, you want to have a new texture. You find some index in this array that's not used, you write a new descriptor to that index, and then you can use the descriptor with that index. This is not compatible with how the original Vulkan model worked for descriptor sets, because Vulkan says you can't update the descriptor set while it's in use. But here we have like a giant table of 1,000 entries, and some of them may be in use and some of them may not be in use. Nobody knows what's happening, right? So this extension allows you more freedom. So the update after bind feature says you can update entries, like if they're not used basically, concurrently by the GPU, even if the entire descriptor set is sort of used. There's probably some language here that describes this more clearly. Well, it's still kind of, anyway, we don't actually care about this for now, because what we want is we have this 300 something textures. We want to create a descriptor set with all of them. We want to bind it to every shader, to the shaders that need it, right? And then we want to be able to indirectly access it using this indexing. So we do need, so for this we kind of need, we mostly need one feature really, which is dynamic indexing, but we kind of also want this one for simplicity, probably, maybe, I'm not sure. We are gonna sort of use this. So this essentially says that we can allocate a descriptor array with, for example, a few thousand, like let's call it like 65,000 entries, right? 65,000 because it's like then you have 16-bit indices, which is pretty good because then you can bit pack them and stuff. Originally, Vulkan says if you're binding a descriptor set, every entry in that set should be correct, which means it should be updated to something. This extension allows you to say, no, for this descriptor, some entries may be invalid, but I promise you, I'm not going to use them. And then the last feature, or the last two features, is dynamic indexing and non-uniform indexing. So dynamic indexing says that I can do what I just tried to do here. So index the texture array with a thing that is not known at compile time. And then non-uniform part means that, so we talked about this in multiple different videos throughout the series, but GPU executes code in groups of threads. So I have this fragment shader which looks like it's doing one thing, but actually what's happening on this GPU is there is probably 64, sometimes 32. On NVIDIA it's basically 32, but the AMD GPUs have two modes now. 32 or 64 threads that form this group, which is not called a group, but it's fine, that all do the same operations, more or less, with some caveats, on different data. And so what could happen, in theory, is the texture ID could be different in different invocations of this pixel shader. Now, this is where there is some, like, difficult parts about how do I know what values can vary within this group. I'm not sure what the official spec name. What is the official spec name here? Oh yeah, okay. The official name is SPRV invocation group, which, you know, there's like, I like the term warp, for example, but for example, the language of this says that it's invocations in a single draw call on a single work group of a dispatch call should have the same value. We are in the fragment shader, so if I have an interpolation, an interpolant that's passed from the vertex or mesh shader to fragment shader, is it like uniform? This is the question which essentially can be rephrased as, if you have a single draw call with two triangles, can these these triangles generate pixels? Can these pixels be merged into a warp? And the answer is sometimes yes. For us, the situation is complicated because, again, as I said before in the very beginning, we have this mode that's using literally one draw call. We have this mode that's using one command, but it's like multiple draw calls because it's a multi-draw indirect. So it's hard to know. But in the fragment shader, I suspect that the way we have written things right now, I don't even know like what are the guarantees for mesh shaders actually, because I suspect that so in our regular path that's not mesh shaded, we have one mesh per draw call. It's just that the draw calls are merged into this one large multi-draw thing. So here I assume that the draw boundaries are respected according to like this language. If I extrapolate and say, oh, maybe this actually means draw call that's like part of the large draw indirect. I don't know. It's hard to know what the actual promises here are without reading the spec. Do I want to read the spec right now? I don't know. Maybe not. Maybe yes. But the upshot of this is this. If you know that the value is uniform dynamically means you can't know like at compile time, but like anyway, it doesn't really matter. When you don't know, so for example, let's say here, let's say because we are using mesh shaders, the answer is, for example, that it's all one draw call and the fragments are going to be merged between different invocations, and this texture ID could actually be different between different triangles that are part of the same processing group or invocation group as they call it. In this case, this feature allows you to still work with these descriptor buffers, with these descriptor like sets, but you have to qualify the access. You have to say, hey, this is not uniform. Actually, this is actually what the shader. Oh yeah, okay. This is what the error is from the compiler is telling us. This is saying the value that you're passing here isn't actually uniform. It seems to not actually be uniform. In which case you can still do the access, but you have to use this qualifier to tell us that it's safe. I don't know to what extent GLSL validates all of this stuff comprehensively. We are gonna find out. I've looked at some environments where things are not validated comprehensively, and so you run into this issue where you write the shader code and it's compiled, but when it executes, the GPU assumes that it is uniform because you forgot the qualifier and does something wrong. And the results of the something wrong are anywhere between different wrong results to like a GPU crash or whatever. We're gonna find out, but the code that I have written here, at least, basically tells me, oh, right, there's probably a fun thing. If I do an indirection through a material, I bet GLSL compiler just lets me do this because I'm going to be sampling from a uniform array, kind of, and then like using the resulting index. It's going to be fun. So if you use this qualifier on every axis, you should be safe if the feature is supported. But it might be slower than not using it when it's not necessary. But the safe default is to always use this qualifier on all axes to things like this. Okay. So this is the exposition. Now we need to actually bind all of this stuff and like try using this and see what happens. There's also some subtlety around, so this is a combined image sampler object. You can also do stuff like this with a non-combined one. I will probably use combined for now because it's going to be easier, but let's set up the extensions first. So we want to switch to the mode where we have this extension, we are using this extension, and we are requesting this feature to actually be able to do all of the stuff that I was just talking about. So for this, we need to change a little bit our initialization code, and then actually, it might be nice to, no, but this will not. I need to be a little bit careful because I don't want to like crash the stream with incorrect code and stuff. Let me first address the device initialization part, and then we'll see what happens after this. Oh, and unlike some features like mesh shading, there's not a fallback for us that makes sense, because we have this pipeline where there's a single draw call basically for mostly everything, and if we don't have some subsets of this extension, we can't do much. So we have to require this and then drop compatibility with some older hardware, which is fine because we don't care about such mundane details. All right, so the plan is activate this extension and then create the set, fill the set with textures, bind it to shader, use this indirect fetching feature. Hopefully things just work. If they don't, it's going to be fun. So every fragment of a triangle will sample the same textures in this example. However, what if you have two triangles, right? If the pixels of different triangles are merged in a single invocation group, then you have a problem. For example, it might be harder to let me put it this way. So like you don't imagine the world where this doesn't happen. Imagine the world where this texture ID is uniform, dynamically uniform, which means GPU processes things in these groups of 32 to 64 threads at a time. For every group like this, the value is going to be the same. Imagine a triangle that is 4 pixels. If you have a restriction that says that this value has to be the same again across the entire group, this is fine, but this means that different pixels from different triangles can't be merged into the same group, because then the value could be different. Which means that if you have small triangles that are like 4 pixels in size, then you have these thread groups, again, not thread groups, invocation groups, the terminology here is a little rough, that is capable in hardware of processing 32 or 64 elements at a time. And in fact, if you use fewer elements, you are using a fraction of the hardware's computational power. But you are forcing the hardware to do this because you have like this fragment shader, etc. It's fairly safe to say that this shouldn't happen because this would be a very, very big penalty on the execution time. And so it's fair to say that even though this is flat, which means flat across the triangle, 2 different triangles will have a mix of these values. For us, the situation is complicated because we don't have per triangle materials, right? We have per mesh materials. But because we aggregate all of this into these giant draw calls, it is actually likely, sort of, in practice, that this stuff is not uniform dynamically. It's going to be a little tricky to test this, but maybe there's going to be a way to test this. But I'm not sure if it's going to be today because we'll see how much energy I will have after we have something going. Okay, so delete this for now. The plan is going to be, I'm just going to have this. So in Vulkan you have sets up at least 4 per stage that specify the resources. We have been using only one set that has this flat like shader specific resources for push descriptors. And the plan is that the set 1 is going to be this indirect thing. We have this assertion here, which built the resource types and stuff. Let us do this. Is reserved for push descriptors. I don't know what I pressed. Go back. And now set 1 is going to be this other thing. All right. One moment. Let us start with the code that compiles and works. Okay. One fun thing with Bindless, by the way, is that because you're telling the GPU or the driver, whatever, that I have this big array of textures, but some of them may not be used, and so I refuse to fill them, this creates issues for validation, because this means that you can have some elements valid, some elements not, and you don't know which ones should be valid until the shader reads them. Because of this, the validation story around Bindless is a little trickier, and so because of this, if there is a problem, if there is a bug, that is catastrophic that we run into, then we will crash the GPU, the stream will die, we will restart the stream, it's going to be fine. But like Bindless, there is a mode that you can enable that does GPU assisted validation. I've never tried it in Vulkan, so I don't know how well it works. We might at some point. But for now, let's just hope that the code that we need to write isn't particularly tricky. So let's hope this is going to be fine. Oh, and I haven't talked about descriptor buffers, but I kind of want to save this conversation because if I talk about descriptor buffers, we'll not get like anything done. So let's just assume descriptor buffers don't exist for now, because there is a second feature that is also kind of for Bindless that we do not need. Our code will not get nicer or simpler or more expressive or whatever if we start using descriptor buffers. But that feature is valuable in some contexts. It's just in our case right now, we don't need it at all. So I will ignore it for now. Okay, so I don't think this stuff is like core at all. I think it's just an ext. Yeah, so what we need to do is when we create the device, we need to say we actually really want, please really give us descriptor indexing. And then there is this crazy feature chain, which physical device descriptor indexing, descriptor indexing features ext, yes, and then hopefully this is right. Features, oh my god, let's call it Bindless as a shorthand. All right, and then the way Vulkan works is you have to tell it what features you want. We'll find out which ones we want, and then you have this insane linked list of like requests for features, which we only have one optional extension so far, which is the mesh shading, and this stuff again we have to have it, and so we will chain this unconditionally and then enable things that we need from this. Okay. We only care about textures, and what textures are sampled images. So there is this, and you are requesting the features that you want. Some of these, by the way, might not be available on some hardware, which we don't really care about. Ideally, you would like check what works and what doesn't. We don't do this right now, so we'll just skip this, it's fine. And then, as I said, there's this whole update after bind stuff that we currently don't need. So for now, we'll just not enable it, I guess. We could enable it. It's just, will be needed. The only reason why we need it if we want asynchronous texture loading, which could be kind of fun. Maybe I'll enable it just so that we don't forget. And the only thing we need really, for now at least, is the images. And this is sampled image, specifically storage images, not... is like a different thing that we don't care about. So let's actually do this. So we'll keep this one, and then we need because of this non-uniformity problem, we need both dynamic and non-uniform indexing. So, oh, I guess dynamic is just implied. Input attachment, uniform textile buffer, storage. None of these are the things we use, so we don't need any of that. So we need sampled image, non-uniform, and that's it. I suspect the way some extensions work is there's like fewer booleans in this struct than you would theoretically need, because it has dynamic indexing bits for a couple resource types, but not everything. And the way Vulkan usually works is they ask vendors, can you support this feature of this extension unconditionally? And if everyone says yes, then you might as well just say, oh, this extension requires it. But if some people say, oh, we can support this but not that, then you want configurability. So this is probably what happened here if I had to guess. I don't have insights, I just have educated guesses. So we need this. We don't need this, but like we'll ask for it so that we remember to like, so that we don't forget to ask for it if we need it later. So we do need this partially bound thing, as I said, because I don't want to like fill the whole thing with like dummy descriptors, which I can't even do easily. So I do want this. We at some point we might do dummy descriptors, but it's like a separate Update unused while pending. No idea what this means. Oh, this is no, okay. All right, let's see. All right, sure. This is kind of, I guess I mixed up what after bind means. Oh yeah, I remember this now. All right, if we, again, we don't really care right now, but I guess there's a difference between this guy. There's a difference between after bind, update after bind, which means you've bound a descriptor set, but then you updated some resources, and update unused while pending, which is the thing I was talking about like 15 minutes ago when I was saying, oh, hey, you have commands in flight that don't use some indices. I guess what I actually meant was this, and I have a separate thing, which is, I know why there's a distinction, but I will not tell you. So partially bound, I already said. Yeah, descriptors in this binding are not dynamically used, don't need to contain valid descriptors, which is what we want so that we don't fill the whole thing. And like again, with one scene, you could say, oh, just allocate 334 or whatever it was, descriptor indices, and it's fine. But I'd like things to be set up such that at some point in the future we decide to load and unload things. We don't have to change any of the outer code. And when people say bindless, they usually mean more than just non-uniform indexing. They usually mean a collection of features, which is what this extension provides, that include most of the stuff that I'm talking about. All right, so I do want this. Let's see. I'm not actually sure. And that is some weird thing. I'm not sure if I want this. Like, I don't... What the heck does this mean? Size is specified when a set is allocated. Upper bound on the size of the binding. This is us, sort of, like it's we have a set that has one binding, which is, we probably, I don't want to hard code this in the shader, so I guess we'd want this. I'm not sure if this is talking about the fact that I suspect this is talking about the fact that when you compile the shader and link the program, you don't have to know how big of the descriptor set you will have. And that's kind of what we want for simplicity. We can work without this, but assuming it's supported, I'd rather have it, I guess. And then a runtime descriptor array, what is that? That's the same thing that I just said. Dear God. Yeah, runtime size. So then this feature is something else? Dear God. Okay, people, we are gonna just enable both. I'm confused as to what exactly they're saying. Like, I'll think about this if the code works or doesn't work. For now, let's just enable this. Okay, so we requested all of these features. Now the device will not get created. Oh, all of these bits are in a different, the princess is in another castle, apparently. So these bits are in features 12. Really? Yeah, they are. And descriptor indexing is here. Okay, I just didn't find it. Okay. All right, so then we are going to lift this. Right, so this extension is part of core 112. And our requirements are, I forgot about this. Our requirements are 1.3, and so we have access to this feature without having to use the extension, which is cool. So then we don't even need to enable the extension, which is also cool. Okay, so the device can be created with all of these bits set to true. Ideally, you check if you're excluding any hardware that you care about by looking at the GPU for database or something like this, but we don't. I assume things are fine. I assume this is like a comprehensive set of features that you can request on any desktop GPU that has been made in the last 5+ years has them. But if that's not true, we'll find out another day. So this is the baby step. The actual real step is we need to create the descriptor set. VK allocate. So we need to create a pool. I had this code, which is not quite what we want, but it had enough of what we want. And I kind of removed it because I didn't want it. But since I want some amount of code that is kind of similar, I want to go back and just to save us some typing, we are going to steal this. It is annoying that this is where descriptor buffer extension would save us a little bit of work, but also would create, I don't know if it's net positive in terms of typing. So, all right. And then we'll need the descriptor pool, but then we'll also need, all right, that's fine, I guess. I'll just inline this code there for now. So I guess I want to do this. Doesn't really matter. Let's do this here for now. We might, well, I guess this stuff has to do with geometry. Wait. Yeah. Okay, I'm not really sure where the best way to put this stuff is yet. It's a little awkward. Some refactoring might be necessary at some point. Okay, so we will say that we want, let's call it 64K. I'm not sure if it's a good idea, but let's call it 64K. And then the way Vulkan, we've talked about this stuff at some point on the stream. This is super basic Vulkan stuff. It's not like Bindless related at all, so I guess I don't, yeah, I don't want to spend time talking about this. We actually only need one pool anyhow. And then what we want is we want this special descriptor. A special descriptor type, but the way you create it, I think, is like using a similar code to the non-bindless code, because all of these. Let me just go back to 1 second. So update after bind, for example. Yeah. So the way Bindless works is essentially you create a descriptor set the same way that you used to create a descriptor set, but you specify all of these interesting flags when you create it, or when you create pools and when you create descriptor sets, I guess. They grafted descriptor, they grafted Bindless on top of like Vulkan descriptors, and Vulkan descriptors were really not made for this, and so it's kind of weird. We are creating the pool that has enough space for 64K descriptors, which is kind of allocating memory, maybe, you don't really know. And then out of this you allocate a descriptor set, and then you write descriptors to the descriptor set. And at multiple points in this process, I'm guessing I will have to specify some flags that actually request the functionality that we care about. So these are the flags that you can specify on the pool. We don't need this. We kind of, as I said, we aren't gonna maybe use update after bind, but I guess we might as well ask for it. We don't need host only. Oh. Alright, that is surprising. So you create the descriptor pool, and then there is vk allocate. One moment. Where is this? vk allocate descriptor sets. But then you specify a layout. Oh god, how the heck is that supposed to work? Huh. Maybe we should have done descriptor buffer. Normally when you allocate, so we have a pool that can house like 64K image descriptors. Normally then what you do is you do this, which is you allocate a descriptor set out of the pool. The problem is this is usually bound to a pipeline state object, which I'd like to not have, but maybe that is impossible. As in, I'd like to just say, just give me like a thing I can bind later that is just an array of descriptors. But maybe that's ext descriptor buffer. So maybe without that, we will need. All right, and then when we create set layout, maybe I should have actually read the spec. Sometimes that is useful. Let me see. Oh. Right. Okay, so this is actually fine. It will actually work like this. And then we'll have two, and then we can bind them separately. So this is fine. We just need to lift more code from elsewhere, I think. So maybe this is fine. Okay, cool. Yeah, so this is all a little bit weird, but it's fine. So our goal is to be able to bind this array of descriptors to the shader. So we are gonna have this binding thing that is binding combined image sampler descriptors for now. A lot of them, but many of them will be invalid. I mean, sure, let's just say fragment for now. We might need compute in the future, but let's just say fragment for now. And then no mutable samplers. So we will have all of this stuff bound to the shader. Hold on. So this, I guess, I really don't, maybe we shouldn't use update after bind for now, because we don't need it. Let's just not use it for now, because we don't need it. So, and then this is what we can create now. Apologies if this is completely incoherent. I haven't worked with this before, and it is more fiddly than I thought it would be, which I should have known better, but you know. But yeah, I think what will work is just this. And then we will be able to allocate a descriptor set out of this set. And this is the thing that we need to do just once, because that gives us everything that we might ever ask for. Where do I specify that it can be partially used, though? Let's see. Descriptor binding flag. Which is what? Set layout binding flags. This is probably chained. Dear God, people. Oof. Let's see. So yeah, descriptor set layout create info, which is this guy. Okay, we are on the right track, I think, even though I haven't read the spec, but I guess who cares? Yeah, okay, cool. Set binding flags, and then we need binding count. I will explain this if this works. Why is this an array? All right, fine. Oh my God. This is a little insane. Okay, I kind of understand. I don't have what? I don't have enough. Oh, I hit Control S. I don't have enough capacity to explain and think right now. So let me. So I don't ignore after bind for now. Although the really important ones are the last two. And these two are kind of around synchronization. It's fine. We don't need them right now. So this, and then this guy chains something else. This guy. If this works, it's gonna be a miracle. And then you create it, and then you allocate it, and then you probably can write to it. All right, I have no idea if this works. Let's just freaking run this. This is painful. And then I will move this to like a function or whatnot. I didn't get validation errors. Well, I'm not destroying the objects. Okay. So what the heck is going on here, you might ask. I don't know if this works yet, but we have successfully arrived. Oh, we can actually, one more thing. Let me bind this thing. And then if that works, and then I will explain what I was doing. So where is our rendering code? It's kind of here. We have two paths because we still have a legacy thing that I'm keeping for now for some folks to profile this code. And then we have this guy. So we need this in both. And then it's just vk cmd bind, no. This guy. Oh, there's a 2. It's probably fine. I don't. Okay, it should be fine. Let me see. Does the layout change? It might be that we need more work, more stuff to rework. 1 second. Yeah. We might have to replicate all of this insanity. I think we'll have to replicate all of this insanity. And I'm now having doubts that we will actually have something on screen today. Okay, yeah. So Houston, we have a problem. Well, I think we need to rework more things, because when we create the pipeline layouts, we need kind of the same code, but not quite the same code. How did this even work before? Maybe descriptor buffers would have helped actually. So we only have a single set layout, but really I guess we just need two. This guy is like, it's just confusing to me that does this not have push? I am confused right now, hold on. Why does this have push constants, but that is separate? So then can I just create one layout that has this second binding set? Okay, yeah. I'm struggling with the question of whether this guy will actually work with like a second layout. It might. All right, hold on. Let me. This is annoying. AF. Oh yeah, but this is why we wanted runtime descriptor binding stuff. Oh boy, runtime array or something. Yeah. Interesting. Descriptor array, yeah. Yeah. Okay. I roughly understand what needs to happen, sort of, but I'm not 100% sure that it will actually work, which is unfortunate, because if it doesn't, that would kind of suck. But okay, so theoretically, if, and I'm not sure that this is gonna work, but if I combine just the first set and then the second set using the same program layout, then what has to happen is kind of this: one descriptor set, and then I have this variable called imaginatively set, which is totally not going to bite me. So let's rename this right now. I'm really hoping for validation layers. So I could, what I should do is I should go and read the spec. But it's already been almost 3 hours and we don't have a rendered picture, so I don't want to go and read the spec. What I wanna, oh my god, no, hold on. what I will do instead is I will write code and then hope it works. So one descriptor, texture set, and then no dynamics offsets, nothing. And then this is, and of course there is like an extra layout, first set, one set, yes. Okay, and then I need the same thing here, except this is mesh task program, and then explanations will come if we don't get crazy validation errors or something. This by itself should work. It's like a redundant binding, but this by itself should work. Hopefully. It doesn't. It's not compatible. So I guess it does want, I guess that makes sense. Okay, so then for this to work at all, oh, but we do have, we did add this array here. So it is in the shader, but it is not in the layout. Okay. Oh boy. The stream is very boring now because it's just me suffering instead of like explaining anything. So we are gonna record uses, I guess, texture set, texture array, which is not uses array texture. It's texture array, I guess. How is it called? Like array of textures? I guess. Oh, yeah. Let's just say descriptor array, because this is the thing we are struggling with. So, and then it has to be uniform. Wait, no. Yeah, I guess. And then if it's set 1, and then this is true. And then when we create this set layout, oh, this is difficult. And this is more than I thought I would need to do. I didn't think it would be like these many modifications to like everything. So it doesn't admit that it is using this, which is odd, because even though hold on. So this is cert. No. Hold on. This is cert used to fail, right? Yeah. So it must be like a different storage class that's not a uniform. Is it storage buffer? That makes no sense. I'm not actually sure why these are different. Oh, I guess maybe need a freaking pause. What? Oh, that can't be right. Oh my God. I'm starting to make mistakes. Yeah, okay. Why would it be a uniform constant? What is this? So this is a uniform constant? Okay, people, whatever. I don't wanna. All right, this is fine. Okay, so, all right, let me let me pause and explain this a little bit. So there's two things you have to connect. When you create the pipeline state object, you have to declare to the API what resources, descriptors like descriptor sets, push constants, etc., you expect to be set. And then there is the other side where you have to create these descriptor sets and set them, bind them. And unfortunately, we have to change both sides. So on one side, we have the shader that uses this array, and we have to parse the fact that it uses this array from sphere v, which I just did. There's some confusing stuff in sphere v, but like whatever. And now that you know whether that is true, you have to then say, oh, if there is this array that the shaders expect, then the array should be bound. So that's this part that I'm working on right now. And then the thing I was doing before this is how do you actually create this object that has all of these descriptors as an array of descriptors that you can then bind. I'm still unclear on some stuff, but I think it will work. And then all of the horrible code here that I was writing, which I'll move to a function momentarily, is just the insanity around how the extension was specified. Because what I want is very simple. I want a descriptor set that contains 65,000 descriptors of a type combined image sampler. And this is the code because, and I'm probably still missing some like flags or some stuff like this, but this is the code. And the reason why the code is insane like this is because it's using Vulkan 1.0 API with these extension structs, and none of this like fits because normally you create a pool and then you allocate a bunch of different descriptors from the pool and stuff like this. Like normally it's supposed to be complicated, but this is complicated for no apparent reason other than the fact that it uses this legacy API, which is what the second extension that I was talking about fixes allegedly. But at this point it would be even more work to like rewrite this using that extension, so we'll probably not do that. All of the things that this code is doing is just, here's a pool with 64k descriptors. To allocate the descriptor set that will map to this pool one-to-one, like that will allocate the same number of descriptors out of the pool, you have to specify the pool you allocate out of. And also you have to specify the layout. And the layout should just be basically an array of descriptors. I'm sure I'm missing something somewhere. Did I specify? Oh, yeah. So we are saying so we have the pool that can give us 65k descriptors. Now we are saying what we want out of this, which is 65k descriptors of this type, bound to only fragment stage for now. I think this can overpromise. Like I think if I have extra stages here in the future, it's going to be fine. We'll test this. And then I have all of these flags that are related to just this extension, but I can't just specify these flags because the Vulkan 1.0 spec didn't account for the presence of these flags. So I have to chain them to pnext of this structure for the driver to know. This is all complete insanity, if I'm being very honest. I haven't realized to what extent things are broken in this area of the API. And like the problem here is This is supposed to be a new feature that is exciting and makes things simpler, but the setup for this feature is like nuts. So that is not great. But if this works, then at least it's better than this not working. So let's finish this part and then take a breather if this works, whether this works. And so before, this code wasn't ready for any of this stuff. This code was just saying, oh no, do I have to? No. This is not the code that I should be changing. Hold on. This is the code I should be changing. So yeah, and I'm still fuzzy on how this runtime sizing works, because I'm not sure what runtime refers to. Like, I'd like to compile this PSO without knowing the number 65K. But maybe I just specify here runtime sized. No, of course not. That would have been too easy. So this binding is this guy, and this guy has the binding type, count, flags, and samplers. Not sure how this works. Yeah, maybe I have to hard code this here. This is not ideal, but not even sure why. Oh, because I remember this for the future. Yeah. Okay. Okay. So I don't love this, but I guess it's fine for now. Oh God, this is difficult to think through. You know what? All right. I have run out of patience. I'm just gonna hard code this and then ask questions later. 65536. I'm sure I haven't read chat. I'm sure in chat there's like, hey, dude, you are doing things wrong. You can just do this and things will be easier. But I wanna explore this madness without hints yet. So I think this is kind of how you do this, and then whenever we call this but ideally only do this if any shader actually needs it. So if binding stage flags. Oh God. All right. Okay, and then and then here we do this, and we'll not bother to destroy this garbage because we'll fix stuff later. I'm tired is the problem. Is one of the problems. One issue is this API is really bad. The second issue is I'm tired. All right. Oh yeah. Yeah. Hold on. This have to match. And then we'll explore this 65K. This is fine. This is like I wanted to write the code that binds the whole array. I'm not sure if I can afford to not say that it should be 64K here. All right, so where does this go? Oh, this is another chaining, isn't it? Descriptor set layout. Yeah, this is the same code actually. Hold on. All right. All right. Okay. Brief pause. Well, so my recollection is you can destroy these guys because of how the ownership works. You can destroy descriptor set layout, array layout here. And then we have a bunch of this garbage left here, which I would think you can destroy descriptor set layout here. I'm not sure what 0 actually is. It's fine. What else did we create? And then descriptor pool we have to keep around because it would be the memory that backs the texture set. And then let's actually call it texture set pool. Oh, whoa. And then let's destroy everything else in the bottom, at the bottom. And then it will be actually time to read the chat. Oh my god. Texture set pool and texture set. Okay. I don't even, it doesn't matter where I do this. Destroy descriptors, descriptor pool. Oh, you don't need to, the sets aren't objects, they're not destroyed, they're freed, but you don't have to. Okay, I think this might be fine. Yeah, this is not how we do this. Zero validation errors. All right, people. People are still watching this suffering, but people are speechless, clearly. Yeah, so promoted to core in 1.2, we fixed that. And then global set layout, yeah, so it is fine to have, it is fine to have a global set layout. Like we could have, the set layout that we have created, we've just created basically twice. We didn't really have to do this. I guess what we can do is, I'm still fuzzy on this runtime thing though. Let me actually look at the spec. Maybe here it will have this. Module uses an array of resources which are declared with runtime array, which I don't even know if it did happen, but it might have. And then this is useless. what I could do is I could just, this is the exact same, with the exception of stage flags. Did we even have to specify this there? This is weird. We aren't using any of the objects that we have created, or we are like binding them to the shaders, but because of the limited validation, maybe this code doesn't work at all. So it's kind of premature to declare victory and refactor stuff, but I'm not sure. There may be simplifications that we could do around some stage flag stuff in particular. Let me boldly attempt to use, so we have spent way too much time wrestling with this API, which is not very good. To be fair, it's not that much code, but it's like just very convoluted. So what we did do in the end is we have created this texture set object, which in theory has 64K descriptors. All of them are invalid because we haven't like filled them. In theory, what you can do is you can update them. Let's try to do that. We are going to do that in an inefficient way, just doing this one at a time, just because I'm very lazy right now because I'm tired. And if that works, then we can try to use that set in the shader. And if that does work, then we'll try to clean this code up and stuff. But yeah, there is parts of this that are fine. There's parts of this that are not fine. And then there's parts that I'm surprised by. Just because I did not expect some of the issues that we've ran into. Oh, I guess it's like the binding is 0. And then the array element is I, and then the descriptor count is 1, and then the descriptor type is combined image sampler. Normally you would not do one invocation of update descriptor sets per descriptor, but if we are going to throw all of this out in favor of a descriptor buffer anyway, then like none of this matters really. So we'll just ignore this for now. Oh, do we even have a sampler? I don't recall. Okay. We have at least one sampler somewhere because we needed like, yeah, this guy. This function will need to become a little bit more complicated. But it's kind of what we need, just not quite the same settings. Let me I'm gonna reuse this old code for now. a lot of the stuff is going to change in the future, so I am spending as little mental energy as humanly possible to get some code running, with an understanding that some of this is going to be relevant and will rewrite code, which is completely fine and good. Okay, yeah, let's see. So it's saying the binding 0 has 0 descriptors in the set layout. How is that possible? Huh? Wait. DST binding must be a binding with a non-zero descriptor count. What do you mean 0 descriptor count? There's probably a bug somewhere above this code. Oh, I should do a print. Have hit the 3-hour mark. I have a little bit more time today, so I will try to finish this. But it's difficult in these cases. I don't have a great sense as to how far we have till the picture on screen, because it could be that we are 3 lines away from rendering something, and it could be that we are 5 hours away from rendering something. It's hard to know. So this is weird. It's claiming that when we... That is surprising. How is it 0? What is it saying? Some crazy flags here which make me think that some weird stuff is happening on NVIDIA hardware around this feature, but it's fine for now. Okay, so I don't understand this. Did they literally do this because this guy doesn't have flags? This is hilarious. Okay. I don't get this. There is a struct with the bind. Yeah, there's a struct that goes to the binding 0 that has a lot of combined image samplers that's bound to fragment stage for now. And then we are creating a set info from it. And then we are allocating. Did the allocation fail? No, that couldn't have been the case. And then this guy, yeah, wait. Set binding 0 array element 0 1 descriptor. It's saying that the layout has descriptor count 0 for the binding 0, but we just created it with non-zero, so how does that work? The problem is the layout, not the so the problem is this guy. That is not what I wanted. Allocation callbacks, yeah, so this is fine. So you specify flags which none of them are around what we care about. And then you specify bindings, one structure per binding. And then inside each structure, that is surprising actually. Oh, is this because we specify this runtime garbage thing? Oh, this is because probably, yeah, is that the case? Probably this flag, wild guess, this flag has to be set differently. Very cute. But now it's saying you can't do that. The hell? So maybe this feature, all right. That feature seems, so I don't understand this feature, but it's not compatible with the descriptor set because one has the flag and one doesn't. Interesting. So when you specify this flag, this is supposed to be like, hey, you know, we will set the count later. But when I actually created a set to write descriptors to it, there's no later. So the fact that I need to remove it sort of makes sense. I'm just creating a descriptor. Descriptor set. But then when I compile my pipeline, maybe right now it doesn't matter because I'm specifying, should I do this? That seems insane. Yeah, which should not work. But the fact that I have to match this. So, okay, I do not understand this. I don't think we need this like right this second. But something is very strange about this. Maybe descriptor buffers eliminate this as well. Or maybe this is for descriptor buffers. And that's why. All right. So this part is very weird. There is too confusing. So I don't know if the code works. We're gonna send an ID and try, or we're just gonna sample like texture 0 or something and see. But I am confused in two places, and they're kind of both around the same thing. One is this flag. I don't understand how you are supposed to set it, but it's also related to the fact that I don't want to specify the descriptor count here, but I have to. So both of these are confusing to me. And really the only way to resolve this is to actually read the spec around this. But okay, so the moment of truth is right now, just in case you guys are wondering. I guess we'll call it UV, because we are going to pass the UV coordinates from both shaders. We have two because we have like a mesh shader and a non-mesh shader. So we are going to pass texture coordinates, and we're going to sample a random texture like a texture number 1 from this array and see if things explode. And we want to be sampling like a different a texture with an index that is dynamic, as we discussed before. But let's just see if this code is buggy. Maybe stream breaks right now. We'll see. Well, that looks like a normal map, ladies and gentlemen. That looks like a texture that we are sampling. And that looks like a different texture that we are sampling. So maybe our code works. So let me commit this horrible, horrible code with broken indentation and God knows what other issues. I would normally, this is why I need to fix Clang format stuff. I would normally refactor the code that we've written like here that creates all of this disaster, but I don't want to do this until I figure out the count thing, because that would change how we refactor this. Well, baby steps towards Bindless. Descriptors maybe work, which we won't find out for sure until we plug the texture indices to. We are attempting to upload all descriptors in a set and index them successfully. And again, this is where the validation behavior now is validating fewer things that it used to. Like it's not actually validating that each descriptor that we are sampling is correct, but we tried a couple by hand and it seems to work. So the final part of the bindless puzzle, the reason why we have went through all of this is that we can now change our mesh definition. Or should it be the mesh draw definition? The way glTF is specified, you could change the mesh definition. But I might want to change the mesh draw definition. Oh, this guy doesn't even access the mesh. Because I erased this distinction early on, that makes sense. And this guy doesn't do it either. Okay, that is cool. So then we are going to change the mesh draw structure. Ideally, this would have like a material index. For this to work, we have to create an array of materials and blah, blah, blah. A lot of work, don't want to do this right now. We might do this later. As in, not today, not tomorrow. Tomorrow we are doing ray tracing because this was painful. But for now, I'm just gonna do a very, very basic thing. I'm going to specify albedo texture, normal texture, and there's also gloss texture, you know, like forget about this. Assume it doesn't exist, it doesn't matter. Why is this not? Oh, does Vec4 align it? Oh yeah, this is the shader, all good. So then, and these are gonna be like -1, I guess. Yeah, these are gonna be -1 if there is no texture there. You could specify dummy textures with 1 by 1, like, you know, 1 by 1 texture for normal maps that aren't there. We're not gonna do this yet because it's more code to write, because we'll need to have a function that like create 1 by 1 texture. You know, more code, more work. We will do this at some point on some future streams. So this is the moment of truth. We are going to add this on the CPU side, wherever the heck this structure is. I guess it's like in 32T, it doesn't really matter. So then we are gonna find code, and the first thing we are gonna do is specify -1s. Should we use 0 as no texture at all? Let's use 0. And then maybe in the future we'll have some index. The problem is accessing an array with -1 index is like definitely a bad idea. Accessing an array with 0 index is a better idea if the descriptor there is valid. Right now it's not, but we can fix that later. So let's actually let's reindex things such that the texture, the descriptor 0 is like a dummy descriptor that should not be used, but if it is used, it will return something ugly at some point in the future. And then, but we'll still have like a branch in the shader that makes sure we don't access it for now, because we know it's not going to contain anything sensible. And then here, we actually, this is a good, let's keep it like this for a moment. And now in the fragment shader, actually, we can just pass the draw index instead of actually let's do it like this then. Where are we? This is the vertex shader. So here we'll pass in like a draw, should be a prefix here. I'll just call it draw, and then we'll pass EV normal. All right, time to invent a prefix. Prefix. Oh, I can just call these guys out, I suppose. So out draw, out EV, out normal, out EV text chord, and then out normal, and then our draw is this guy. And then we will be able to access all of the other data in the fragment shader by just reading that thing. So then here, it will be draw ID. Let's call it draw ID here as well. We are very close to actually like seeing a textured scene, which would be the which was the goal for this stream. So keep this for now like this, and then from here on we will be able to only change the fragment shader and not worry about like the different shaders that we are using. Ideally this value would be specified per primitive. It uses is flat. It might be equivalent in the, I'm not actually sure. I'm not exactly sure what the semantics are in the mesh shader. The complication that we have right now is that we have two very different shaders that do vertex processing. One is vertex shader, one is mesh shader. And then only one fragment shader is shared between them. So that's like annoying-ish. But I guess it's fine, sort of. It's not ideal, but it's like not terribly bad necessarily. So, and this breaks debugging, which I guess is fine. We don't really need it as much. Maybe we'll fix it later somehow, at some point. We have like a mode that visualizes like individual meshlets, and that mode will be inaccessible for us, which is unfortunate. All right, so command draw ID is what we need here. I don't know if this works. It does not. Let me copy paste this stuff. Let me copy paste this stuff. All right, the moment of truth. Oh, let me switch 1 second. All right, the moment of truth. If this works, then we are done. If this doesn't work, then we are not done. So we have the draw ID in the fragment shader, which, by the way, we can actually output if we want, like, I should have this code somewhere in like shared space. But if we want to, we can do the following now. We can take the draw ID in the fragment shader, we can hash it, and then we can write it out, and we can actually define this so that this works. One moment. And then this should show us the draw IDs of the objects, which should be consistent between the two visualization mode. So this is actually good, right? So now we can switch back between two pipelines and we can see an ID of the draw call converted, like a virtual draw call. We don't have draw calls in one of these modes at all, but it's an ID of the instance of the mesh essentially, which is consistent between two modes. Okay, so now we are ready to save the texture index, fetch from the texture, hope it works. We have a sampler settings that are broken, we'll fix that, and then if all of this works, we'll finally be done, and this will be an insane speedrun. Oh, and except the descriptor count thing is broken. Okay, we are close, we are almost done. This is going to be a 4-hour stream because it's already 3.5, but it's fine. Everything for the gram. So, okay, so we need to initialize the indices which we have added to the struct in the glTF path somewhere. So wherever the heck this is, this is that. The indices. Yeah, so this is gonna be easy because node mesh has, does it not? Oh, the primitive, not the mesh. Oh, the primitive, hold on, how do I do this then? Is it just, oh, this is awkward, hold on. Hold on. We do this weird remapping now here, which means the indices are off potentially. And that's annoying. I should have done this differently. Because it attaches a size. Hold on. Oh, this will be incorrect. If range second diverges from mesh prim count, this will be incorrect, but this is fine. I'll fix this. I just don't want to do this right now. All right, so draw albedo texture. If we have a material and it has like where is this PBR? Is this like inside of this guy? Yeah, okay. And then this is the texture. And then this gets us the image, and then we use glTF image index Oh boy, what happened here? Okay, I think this is it. And then otherwise it's, oh, we decided it would be 0. Wait, what? Hold on. So if we have this texture, oh, this is an extra breeze. Okay. And then the same thing with normal texture, except that it's stored like here. No, wait. It should be a texture index, actually. I'm assuming this function will be upset if we pass a null pointer in. I don't recall, but this is likely. Yes, it will be upset. Okay, and then ideally we validate. Oh, we parse the texture paths later. You know what, it's fine. All right, so this gets us the indices, I think. Okay. The final step, the single line or 2 lines or however many lines that we actually were doing all of this for is this. We have the draw ID, which means we have access to the object that has the indices. And we can now sample the textures once we use like the extension and whatever. So the way that we will do this is we'll say albedo is, I guess, defaults to like 1, 1, 1, 1. And then if the IntelliSense is broken, I'm surprised it even works. So if the albedo texture is greater than 0, because we are now using 0 as this like doesn't exist index, then we will sample textures mesh draw albedo texture using the UV. And then we'll do the exact same thing for the normal map. By default, it's RG blue, like this, for example. It doesn't really matter. And then if normal texture is here, then we'll sample the nmap. And then we will use the albedo value as our output and then hope things do not explode. Right, so now this is where the compiler is telling us, hey, you're using this expression that has the value that is sourced from, this is actually, oh, I forgot, oh my god, I'm so happy the compiler detected this. This is the case I was talking about earlier when I said maybe this is the case where the compiler doesn't detect this, but it does. Okay, so the compiler is saying you are using your index in this array with a value that we don't think is uniform. So you should fix it. And the way you fix it, the way you can fix it is by saying this, by using this like non-uniform X thing, like this. So you just wrap the index into the thing. I assume there is also another way to fix this, which will not work in our case, which is to tell the compiler that this value is actually uniform, but I don't know if this is a thing. Let's see. No, there's only, interesting. I'm surprised you can't force this. Maybe there is some other different extension. Anyway, moment of truth. Does this work or does this crash the stream? The sampler settings are broken, but that's fine. Man. Oh, this is as if all textures are 0, right? Let's confirm this theory. Did I not do this correctly? Huh. Oh, it's because this file NVIDIA is using a deprecated extension which there's two ways to specify the diffuse texture, the albedo texture, whatever you want to call this, in glTF, and NVIDIA is using a deprecated version in that scene, which is not ideal, but it's fine. Moment of truth number 2. Well, does this look correct? No. Oh yeah, okay. And then we did this change, which is things are like one base. You know what I mean? 0 is an invalid descriptor. 1 is a valid descriptor. All right. And then the final thing is the sampler settings are wrong. All right, to fix the sampler settings, we need to override a bunch of stuff. The helper is becoming less useful, but I guess it's fine. So I want this to be a parameter. And then I want this, this to be a parameter. This is awesome. I can almost be excited, except that I need to finish the last few steps. Should I? It doesn't really matter, I don't think. I think this can be FLT max. Well, let's keep this. 16 is enough. Okay. So we have the sampler that is used for the pyramid sampler, which has to be a very, very, very specific version. This is like 0, right? Yeah, but I guess it's an enum. One moment. And then we have the other sampler, the one that we need to use for the scene, that should use full meep mapping with trilinear filtering, etc., anisotropic some other day. All right. The reason why you see beautiful pink colors right now is that the glass, I guess, is not like, materials are complicated in glTF. Today is a texture stream, not a material stream, so let's for now have some more muted color that is less like eye-catching. Okay. And then the final step. Is this too much? All right. It's almost 4 hours. So one final step is the downside of using albedo is you don't see bugs in normals. So I want to do the normal map, but to do the normal map, I need to do the tangents. To to do tangents, I need to change the vertex format, but we are done, people. We have things working. All of the other stuff is just like I'm gonna add tangents right now, but this is very mechanical and it just will work. It's fine, like there shouldn't be any issues. The steps that we were doing so far were stressful because there was a risk that something will go wrong. And then you never know what is the consequence of this. Like, do things explode? Do things hang? Is there a validation issues, etc.? But we have persevered. Things are fine. And that is awesome. I guess this should be, and this is 254 technically. We haven't bothered doing tangents, then there's no tangent space in OBJ, but there is absolutely tangent space in glTF. And so I just want to be fully done. So I wanna plug that through. And are they always 4? They are always 4. Thank you, glTF. Dun, 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 dun. Okay, awesome. If I don't look happy, it's because I'm tired. But this is done. I changed that, and then change 15 shaders. Hold on, so this is back 4 tangent, and then this is tx, ty, tz, and then oh man, okay, tw back 4. The reason why tangents have 4 components is that it's a vector, but there's also the 4th component, which what am I doing? Which specifies the winding, like if the tangent space is like sort of right-handed versus left-handed, which affects how you reconstruct the 3rd vector that you need for the space, which we will need because that is how you do normal mapping. The last time I wrote a normal mapping shader was in like 2013, 2014. It's like 10 years ago, but I'm reasonably sure I remember the math. Not quite sure, but like it's not too hard. Okay, so this was the one shader, and then this guy needs the same thing, and then this guy needs, I don't know why this order is weird, but okay. Okay, okay, and then this See, I can't even freaking type anymore because I need a break. But we are gonna power through, and then 10 minutes for questions, and then we are done. So we theoretically have tangent space for all the good that it's gonna give us. So we are going to compute a vector called bitangent. Some people call it binormal. These people are wrong. And then this is TBN, so NT, so this should be a cross between normal and tangent. And then times tangent dot W, I think, because I think it will flip things correctly. You might want to normalize all three really, because there's oh no. I think the better, yeah. And so then, okay, so then the normal, well, the it's awkward because we should probably call these like in. Don't like these prefixes. They're aesthetically unpleasant. So I don't know. It's a terrible name. It's fine though. Yeah, I think this was actually correct. Hey, give me. All right. So what you need to do. What you need to do here actually is you need to do this math, because this gets you from 0, 1 to -1, 1. And then you just do x times t tangent, and then y bitangent z normal, normalized result. See if that results in a normal that seems directionally correct. Well, it's subtle. I don't know if you can see this on the stream. Well, I guess you can see this on the building on the right. All of these grooves are not geometry. And the way you tell if things are sort of, it would be useful to disable enable, but I kind of remember how the colors were. So if you look at the solid green, it's kind of the vector going up. And in the grooves on the bricks, you see that on the top of the brick, it starts with the same, like above the brick, there's the same solid line, solid green line, and that also points up, which makes sense because the bricks are kind of like outdentations, not indentations. So, you know, probably, I'm sure that there may be bugs here, but it's probably sort of correct. And then the final step is we'll do like albedo times, yeah, this, come on, dot product normal, some like random light vector kind of, and then plus like 0.1, sure, why not? Oops, wait, no. All right. And this is a terrible light direction. I forget, I had to like flip it against some axis for it to be less terrible last time. I don't recall which axis this was. I guess good enough. Now you can flip between LODs and see that nothing is flickering. It's still a terrible, it's like, is it going? Maybe I should flip it against C as well. Okay, that's better. I have a light direction in the glTF file, but I'm totally not getting that. That is it. The one mystery remaining is this dynamic descriptor size thing that I do not feel any motivation to fix right now. So I think we'll call it here. All right. Oh, let me keep this running and then look at the chat. Oh my God. Yeah, there's obviously a lot of issues in the scene, right? So one issue is there's no transparency on the plans. And as I talked about, then the other issue is there's like on the left door here, you don't see the glasses. This is because the glass material is double-sided. So you only see it on one of the doors, right? Because like on one it's backface count, on one it's not. Because one door you see the front of, one door you see the back of. And then of course the glass is translucent. To fix this, we need to do double-sided support, but also we need to do translucency support, which requires blending, but also it requires effectively disabling occlusion culling. So, or disabling occlusion, disable writing to the depth buffer, I guess, more than disabling occlusion culling. Because you can still do occlusion testing just fine. I need to think it should be fine because it's just, yeah, I think that's just rendering, basically just rendering the objects with different like blend settings and whatnot. And different culling modes. Oh, right, yeah, double-sided requires disabling cone culling. So it's like a little bit of tweaks, and a little bit of extra code, but not too bad. And then the plans, you could solve them the same way, but probably what you do there is you do alpha testing with stochastic like alpha rejection or something like this, which would just be a shader tweak, except that, you know, it's been 4 hours. So I think we are not doing this today. But we see and then there's a third texture, maybe a fourth texture, definitely a third texture that we aren't using, which is the gloss map. But it's like not terrible, right? Oh, the other thing is this lighting is broken-ish. You kind of don't see this, but you can spend like an unlimited amount of time tweaking the shaders. So this is not going to be very correct, but yeah, but this should be better. There's a right way to do this, which we will not do right now, but this is a little bit better. This smooths the highlights a little bit, and it's... Wait, did I do the right thing? Because this would be a linear 2. Yeah, it's kind of... The correct math here is different, which we'll cover at some point later, but... this is not... too bad. I'm actually doubting this now. No. Yeah. This is correct. I might want to compensate a little bit for this. All right. So, is there a hint in the chat as to what the heck is going on with the descriptor counts? Because this is the only like insanity. Yeah, but like I am using an unbounded array in the shaders. This is the confusing part to me. So the shader didn't have to specify the size. But actually, if I recall, the way this usually works is if you don't specify the size in the shader, but you do specify this size when you create the pipeline state object. Do we specify the layout actually? When we create the PSO, I think we should, right? Oh, we don't. Wait, we don't? No, this is not the PSO. Yeah, right. So like right now the driver, when it compiles the PSOs, it has an information about the descriptor count because we create this array layout with the 65K descriptors, and then when we link the PSO, it knows all of this. And I thought that this flag that we tried to use unsuccessfully is like fixing that, but it didn't work. And I was the way it didn't work didn't make sense to me. So okay, let me commit this. So this is, we have tangents working, we have texture sampling working, we have a fragment shader, everything. So this is basically mostly just shader work. This Bindless textures work. We now specify the texture to sample in the draw call structure, and also have tangents fully working so that we can do basic normal mapped lighting. All right. So yeah, so like this is the one thing that I'm confused. Yeah, so the reason why I didn't do descriptor buffers is I opened the spec yesterday on descriptor buffers, and I looked at this and I was like, it felt like it replaces a lot of complicated stuff with other complicated stuff. And like, it wasn't clear to me that I actually want to do this. The reason why descriptor buffer extension exists is because everything that we've written so far still works in terms of descriptor objects. And this is not the model that is convenient when you, for example, emulate Direct3D12. Because Direct3D12 has this model of resource heaps where you can, for example, specify multiple different resource types in the same heap. We don't care, we just want an array of textures, but they want a bunch of descriptors where some are textures and some are buffers and some are UAVs and stuff like that. Which in that world, this model that we have been using is just like not workable. But it wasn't fully clear to me if the descriptor buffers are solving the ergonomics issues, and so I didn't want to do that. But I underestimated the amount of the ergonomics issues through the normal path, so like maybe we should have done this, but it's fine. I don't think so the goal for the project, I don't know if there's a goal for the project, but now that we've suffered through all of this, I'm gonna attempt to steal a little bit more time and fix this count thing is boggling my mind. I want to understand this, but so let's go back to the plan. This is the plan. So this is fully done, except that, okay. So this is done. This is not in progress. We are done with bindless textures. There is nothing more we need to do. The only thing other than fixing the stupid descriptor count thing, we could improve the way, like there's minor code refactoring we shall just do off stream, like it doesn't matter. We can improve the way how the textures themselves are uploaded by making it less synchronous and stuff, but it's like fast enough that it doesn't actually impede us in any way. There is more work that we could spend on materials. This is the stuff that I was just talking about, right? Actually doing translucency. There's like even more basic stuff. glTF files have a factor, a color on materials that we aren't applying right now because we are just sampling the texture. So probably we should do material struct, index that, you know, like it's all kind of straightforward. I don't actually care an insane amount about that. The reason why I wanted to do bindless was twofold. One is I wanted to understand the space better because I haven't used the extension before. Like I knew mechanically what things should happen in the drivers and in the GPUs and stuff like this, but I was unfamiliar with the API surface. Now that I'm familiar with the API surface, I can't say I like this a whole lot, but you know. And then other big thing I want to do is ray tracing. We will start doing ray tracing tomorrow. I don't want to do a 4-hour stream tomorrow, so it is unless ray tracing goes way faster than the stream today, we might not get to like a nice result or to a result. But the goal for tomorrow would be, if possible, to just do shadows from the sun with the code that we have, just like casting array. But then I want to do more stuff with ray tracing, and some stuff that I want to do with ray tracing wants maybe a gbuffer, not necessarily a gbuffer, but you know, like once you start doing denoising and restir and stuff like this, the model of the fragment shader outputting the final color to the screen becomes problematic, and so maybe we will do this. But you know, any of this stuff will happen. So there's going to be a stream tomorrow, same time, hopefully not 4 hours, and then there's not going to be streams throughout November. Because I'm gone. So whenever we pick this up, we'll see. Maybe I have other thoughts, but that's kind of the plan. So in a sense, I guess this thing should not be here because we are doing ray tracing. We are doing ray tracing tomorrow, and then there's like materials and denoising and God knows what else. All right, so yeah, all right, nobody knows what happened. Okay, the only thing, because it's just, so I've talked about the binding features. A couple of which didn't need, and so I don't care. One of them we used right now, this non-uniform thing, which without this, you know, we couldn't have done what we have done, so that's cool, that's okay. And then there were 2 more features that we have enabled. 2 more, actually. Well, we enabled update after bind, but we didn't need it. We did need this one and we used it, so that's cool. Update unused while pending, I talked about this. We don't need it because we don't update anything after we start using them. But if we do streaming, which could be cool because it's a way to asynchronously load textures while you still see the results. So that maybe we'll use, we'll see. Partially bound we do use actually, because that's what enables us to fill 300 textures without getting validation errors. And then we have these 2. RIA. So this one, this is what I thought. So this one is fine. This is what we actually are using. This is what allows us to not have the description in the shader about the number of descriptors used, but to still have the shader compile. And that requires this feature, which is then used when you create the pipeline state object, I guess, to like correlate these 2. This is the missing piece. This is the thing where at this point I don't understand what the hell is this doing, and whatever it is doing, we couldn't get it to work. So what is this? Binding variable descriptor count. It precludes the usage of dynamic, which I don't care about. What is it doing? The size will be specified when the descriptor says, oh my God. Wait. I get it. I see. Oh, and you specify an upper bound, which is why you can't specify 0. I see. Got it. Okay, the puzzle is actually very simple. I see. The full value, upper bound and the size. So unless, all right, unless I'm misreading this, this is actually fairly simple. You still need a number. It's just that you could allocate less. Interesting. So what you can do with this, which I guess I want, I don't know, I don't care too much. It doesn't, with the baby numbers that we are using, it doesn't really matter. Once you're using like a million descriptors, it kind of starts mattering. So I think this is what this allows you to do. Let's try this. So suppose we have a limit right now of 65k textures. Suppose we wanted to have very little limit. Let's say we want 1 million. Hopefully nothing explodes. If the stream dies right now, then we are just done and like thank you and stuff like this. But you know, so let's say that we want this value to be like much larger, right? This will work, I assume. Did I specify the bit? I didn't, but I might as well. Now it doesn't really matter because this is not the point. Okay, I think I get it now. Okay, so this I think will work. No, or not. Oh, no. This is why we had to disable this thing. Interesting. So how do I make this work? Okay, no, I understand the feature. I'm still confused as to how to make this work though. Interesting. Because, okay, so this will work, I assume, I hope. Let's see. Okay, so this is fine, right? We just increase the number to like 1 million, it doesn't matter. The issue is we are allocating a descriptor set of 1 million descriptors. And that's a bunch of memory. I believe that's like 32 megabytes of memory. Don't quote me on that. Maybe it's 64. I think it's, don't quote me on, it might be 64. 32 sounds insufficient for combined descriptor. It might be 64. It's a bunch of memory. What if you know that you want to use fewer descriptors? You could reduce this number, but that requires you to rebuild the pipeline state objects and stuff like this. So that's kind of a problem. It interferes with the caching, etc. It's not ideal. It would be nice if instead you could say, oh, I only am going to allocate, for example, my scene uses 1,000 objects. Okay, so I'm only going to allocate 1,000 objects. So this would be like a max descriptor count and an active, let's just call it active descriptor count. So let's try to go through with that. To do that, we need a smaller pool because the pool is where the allocations usually happen. So we need to say that this pool only has this much. And then the pool size is just this big, that is fine. Oh, max sets actually should just be 1 here. I'm not sure why this is a bug. So then we create a descriptor pool. And then when we allocate out of this descriptor pool, we only want to allocate this much. So again, here what we must do is we must say, wherever the count is here, we say, oh, we actually only want to create this much, right? The issue is this will fail, I think, I hope. Yeah. This will fail when we bind because we have a mismatch. We have a shader pipeline state object that's built with 1 million and the descriptor set that's allocated with 1,000. And you can't do this unless you have this flag. This flag says the number that you specify when you create the layout is like a promise for the future that this is the maximum that you will ever need, but you could have smaller number, smaller, like you would have fewer. Oh, I bet you have to chain some stupid thing when you allocate. No, that can't possibly be right, can it? So, right, but like in theory, what should happen then is, maybe I have to only specify it here. This is confusing. Oh, the other way this might be correct. No, but when we allocate, we just specify the layout that we allocate. We don't specify, it must be here somehow. It's also possible this only works with like descriptor buffers, but I find it hard to believe because it's part of the original extension. So yeah, okay. But like I hope it makes sense. The reason why this is valuable is it allows you to build the shaders with a very high potential limit that you're never actually gonna hit, as long as the hardware still theoretically supports it. So this is a whole separate problem with Bindless where it's not clear what the limits are. But yeah, the issue is there's something missing in how I'm using this flag. I assume you should set it on both. It should be necessary here. And I guess it is necessary here because the validation layers complained. But then somehow this breaks updating, and this is what I don't understand. Aha, we found it. That is one more stupid structure that you have to chain to some other thing. I bet. Oh no, support. No, this is not. No, this is querying. This is querying some stuff. Where's the function? Yeah, okay. No, this is not that. Yeah, this is that. When you allocate, you're supposed to ask. I see. Yes. Yes. All right. Thank God. This is why it was saying that it's 0, even though the validation error is not clear here, but it's fine. So. You are supposed to specify this amazing struct, whatever the name of this would be at this point, like set allocate count info or something. And that thing is gonna tell us that in the one descriptor that we want, I see, you need, this is like a uint. Okay, this should work. So, and then you have to chain this to this, no, not to this guy, to this guy. Okay, so this will tell us that instead of allocating however much the layout says, we are going to allocate this much. And then I think probably the binding stuff should still be created with like the max limit, I assume. I'm not sure. Let's test this. So I assume this will not work because of a validation error. Yeah, this is actually a good error message. So when we create the layout, which is this, we specify the maximum theoretically possible limit. And then when we allocate, we only specify 10.4. Thank God. All right, that resolves this conundrum. And again, the reason why you'd want this is to conserve memory. We could just allocate a million descriptors. It's fine. It's like 60 megabytes, 30 megabytes. Who cares? We are using a lot more on a lot of other stuff. But, you know, it might be inconvenient. It might be an issue on low memory platforms, etc. Like, it's not always the best. So this allows you to have two numbers. One is the theoretical possible number that's kind of baked into the PSOs. And so changing that is difficult. And the other one is the actual number that you care about. And this one we can even say now this doesn't have to be like a constant. It could be the number of textures. So like the 340 whatever, right? Texture path size +1, because remember we have this +1 thing for the like invalid index. Okay, that resolves this particular problem. I will submit this as this, and then I'll like do a minor refactoring off stream maybe tomorrow morning, or I don't know. I need to go touch grass and meet someone. So day 23, resolve the conundrum with variable size descriptors. These can be used to reduce the memory footprint of the descriptor pool without changing the like limits specified during PSO creation. And now the layout that we use is the same between this code and that code. And so I guess you know what the heck, 3 hours, 4 hours, 2 more minutes. Oh, but stage flags in here. No, you know what? Refactoring later. That's it. All right, so let's marvel at the fruits of our labor. And declare a smashing success, except that it took 4 hours, 20 minutes instead of 2 hours and a half that I was hoping it would. But you know, software engineering is like this sometimes. I did not expect this API to be bad, but it is bad. But you know, did I press something? Okay, cool. All good. All right. It will be fine if this crashes right now, but I don't think it will. Yeah. So this is how our kittens look like right now. We have the texture that's not set, and we have shading, but our light is like, our light direction is who knows where. So it looks a little bit weird, but you know, it's still the same code works with no changes. I actually, it got slower for sure. Significantly so, I might add. One moment. Yeah. We now use way more attributes per vertex. We only had one, which is a color. And now we have UVs, normals. We do the prim ID, the draw ID, which like there's a better way to pass it, but I think it requires shader bifurcation maybe. So we created some problems for ourselves that we could excitedly solve in the future. Obviously the fragment shader is heavier, but on this scene there's so many triangles that probably the triangle cost, the vertex cost, and rasterization cost is still dominating. But yeah, like this is slower than it used to be. I don't recall what the numbers were though. It's not way slower. I do not remember what the numbers were. I guess we can find out. And this is why you don't use globs, people. Globs are terrible. Okay. Okay, actually it's not too bad. This is 283 and that thing was like 320 something. Okay, actually 3 here for whatever reason. It's fine. So yeah, so it got like 7% slower-ish. So it's not even that bad. It might be that fixing the draw ID problem doesn't fix things. There's ways to render. There's ways to improve this in the future, but like I think once we do ray tracing, all of the performance concerns about rasterization are going to be irrelevant because this is going to be the actual bottleneck. Anyway, that is it. We are very done for today. The stream tomorrow is going to be at the same time, hopefully not the same length. We will see what happens. I really want to go through the ray tracing up until we see the result on screen. And I'm just hoping that it's going to take less time. All right, thank you everyone who have persevered through this terrible journey. It was fine. Like, we didn't hit any severe problems with the ecosystem, etc. But this is just sad because this is convoluted, the amount of flags is convoluted, like the amount of options. Whenever you have an extension with like 16 booleans or whatever it is in the feature struct, you know, I guess you should know you're in for like a world of trouble. All right, so code is gonna be on GitHub. I'm gonna update playlists like in a few hours. And stuff. Thank you everyone. Whoever wants to join the stream tomorrow, you are welcome. I hope it's gonna be less stressful, but it actually might be more stressful because this at least is, you know, I understand all of the underlying mechanics really well. I just was very clueless on the API, and the API is what's the problem here. Tomorrow is going to be like, I have fairly little context on some of the stuff that's going on there. So we will see how that works. Until then, thank you everyone, and bye.